Hello, and welcome to the Sleepy Voyager. If you enjoy quiet, thoughtful documentaries that help you drift off while still learning something wonderful about our universe, please tap subscribe and turn on the little bell. Your support helps me keep making calm stories like this one. Thank you and sweet dreams as we begin. An interstellar object is a small natural body, like a rocky asteroid or an icy comet that comes from outside our solar system. When astronomers say 3-eye Atlas, they mean the third interstellar object discovered, that's the 3-eye, and that it was first found by the Atlas Survey, which is an automated telescope system that scans the sky for moving objects. Interstellar objects do not orbit our sun the way planets and regular comets do. Instead, they follow a one-time path that cuts through our solar system and then continues back into deep space. This path is usually shaped like an open curve called a hyperbola, which tells scientists the visitor is not gravitationally bound to the sun. In simple terms, it is just passing through. We usually find objects like this with computers and telescopes, not with our eyes. Survey telescopes take many pictures of the same patch of sky night after night. Software compares the images and looks for tiny dots that have changed position. If the dot moves in a way that does not match a satellite or a known asteroid, astronomers pay attention. They measure the object's position over several nights and calculate its speed and direction. If the numbers show the object is moving too fast to be a long-term member of our solar system, it gets tagged as interstellar. This checking process is careful and repeated to avoid confusion with planes, satellites, or weather effects. From Earth, an interstellar object is usually very faint. It reflects a small amount of sunlight, and it is far away. To learn about it, astronomers record how bright it appears, how that brightness changes, and what colours it reflects. Changes in brightness can mean the object is spinning and has an uneven shape. Colour clues can suggest whether the surface is more rocky, more icy, or covered in dust. Sometimes a fuzzy glow forms around it, called a coma. That happens when sunlight warms frozen material and gas escapes, carrying dust with it. If there is no fuzz and the object stays sharp like a point, it may be more asteroid-like, with little or no surface ice. Because interstellar objects are new to us, size estimates are wide. Astronomers cannot easily measure their width directly, so they estimate it from brightness. A darker surface needs to be bigger to reflect the same amount of light as a brighter surface. This means the size can be uncertain by a factor of several times. Still, most likely sizes are small by everyday standards in space. Anywhere from tens to a few hundred meters across is common for the kinds of faint objects surveys detect. Even at these sizes, they're important because they carry material that formed around another star. The path an interstellar object takes through our solar system is mainly controlled by gravity. The sun pulls the strongest, but planets can give small nudges if the visitor passes close to them. A slight jet of gas from a warming surface can also act like a tiny thruster and change the path a little. Astronomers include these effects in their models and update the orbit as new measurements come in. This is why you might see the predicted path get refined many times in the first days and weeks after discovery. The goal is to predict where to point telescopes so we can collect as much data as possible before the object becomes too faint. Why do scientists care so much about a small dim visitor? Because it carries information about how other planetary systems form and evolve. The dust and ice on its surface record the temperature, chemistry, and history of the place it came from. By comparing its properties with comets and asteroids that formed here, we learn what is similar and what is different across the galaxy. Even a few measurements, like how quickly it rotates, how reflective it is, and whether it releases gas, can help test ideas about planet formation and about how small bodies get thrown out of young star systems into interstellar space. Finding one of these objects also shows that our survey systems are improving. Years ago, we missed visitors like this because our coverage of the sky was slower and our software was less sensitive. Now, with automated searches running every clear night, we can spot fainter and faster objects. This steady progress matters for both science and safety. While most interstellar visitors are harmless and far away, the same tools that detect them also help us track near-Earth asteroids that could that could one day come close to our planet. The process, take images, find moving dots, calculate paths, serves both purposes at once. When an interstellar object is labelled with an official name, each part of the name is meaningful. The number 3 marks the discovery order among interstellar objects. The letter I stands for interstellar. The survey name, ATLAS, identifies the project that first reported it. This naming system helps scientists organise data and refer to the object in papers, databases, and end observation plans. It also helps the public and the media talk about the same thing without confusion. Simple, consistent names are useful when many teams around the world are taking measurements at the same time. Observing time is limited, so teams coordinate. Large observatories may take spectra, which split the light into many colours to show what chemicals are present. Smaller telescopes may do light curves, which measure brightness over time to study rotation. Space telescopes may observe in infrared, which can reveal heat and give a better estimate of size. Radio telescopes might listen for gas like carbon monoxide escaping from the surface. Each type of data fills a different piece of the puzzle. Shared results build a more complete picture than any single telescope can provide on its own. For the general public, the most important idea is simple. This is a natural object from another star system that is passing through ours. It is not a spacecraft, not a signal, and not a sign of danger by default. Its speed and open path mean it will not stay. It will brighten a little as it comes closer to the sun, then fade as it leaves. Most of the time it will be too faint to see without a telescope. If it produces a tail, that does not mean it is large or threatening. It only means sunlight is warming some surface material and turning it into gas and dust. Tails are normal for icy bodies. Scientists do consider many possibilities, including low probability risks, because that is part of responsible study. But the most likely outcome is calm. The object passes at a safe distance, we collect data, and it moves on. The value lies in what we learn. Each visitor adds to a growing sample of worlds in miniature from other suns. Over years, this sample helps answer big questions. How common are certain kinds of ices and rocks? How do small bodies get ejected into space between stars? How do their shapes and spins change after millions of years in cold darkness? Bit by bit, answers emerge. If you are curious how to follow discoveries like this, observatories and space agencies often post updates with simple diagrams showing the path and brightness over time. You may see a plot that looks like a shallow U-shape. That shape shows the object brightening as it approaches, reaching a peak near its closest point to the Sun or Earth, and then beading as it recedes. You may also see a map of the sky with a line that marks where the object will appear on certain dates. Amateur astronomers use these charts to plan observations with backyard telescopes and cameras. In the end, an interstellar visitor reminds us that our solar system is part of a larger neighbourhood. Material does not always stay where it was born. Gravity moves things around. Some pieces escape and travel for unimaginable distances and times. When one of those pieces enters our view, we have a chance to learn from it. With simple tools, careful images, patient measurements, and clear math, we turn a faint moving dot into useful knowledge. That is the heart of this chapter. What it is, how we find it, what we measure, why it matters, and how it quietly connects our home star to the wider galaxy. It begins with pictures of the night sky taken again and again from the same spot like flipbook pages. Survey telescopes sweep wide areas, taking short exposures every few minutes. Each new image is time-stamped and stored. Computers then line up the stars between two images and subtract one from the other. Stars disappear because they stayed put. Anything that moved leaves a tiny leftover dot or a short streak. This is called difference imaging, and it is the first hint that something unusual is there. The system flags all the leftovers and sends them to a classifier that tries to tell the difference between real objects and things that only look real, like camera noise, airplane flashes, or glints from satellites. When a leftover looks promising, the software groups nearby, detections from the same night into a small path called a tracklet. Think of a tracklet as 3 or 4 dots that line up in the right order across an hour. If there are enough dots and they form a straight, steady motion, the system says this might be a real moving object. At this stage, the candidate is still just that, a candidate. Many things can fool a telescope, including thin clouds, wind shake, and the faint trails of geostationary satellites. To reduce mistakes, modern surveys use machine learning trained on millions of past examples. The model scores each detection and downranks the ones that look like noise. Humans still check random samples to make sure the software is not missing real objects or letting too many fakes through. The next step is linking tracklets from different nights. If the same patch of sky is revisited the following night, the system tries to predict where the moving object should appear, given its motion from the first night. If a new set of dots is found near that prediction, the tracklets are linked. With 2 or more nights, an early orbit can be estimated. This orbit is not final, it's a rough guess that says how far away the object might be and how fast it is moving across space. The math behind this is called initial orbit determination, and it has been used for more than a century, upgraded with modern statistics to handle uncertainty and measurement error. All measurements are turned into sky coordinates, numbers that say exactly where the object was in right ascension and declination at a given time. To make those coordinates accurate, each image is calibrated against a star catalogue. This step is called astrometric reduction. The computer matches hundreds or thousands of catalogue stars in the frame, corrects for tiny distortions in the camera optics, and then pins the moving dot to a precise location on the celestial grid. The quality of this step sets the quality of everything that follows, so surveys invest heavily in good optics, stable mounts, and careful software. When the orbit gear seems stable, the discovery is reported to the Minor Planet Center, the international clearinghouse that collects observations of asteroids and comets. The MPC assigns a temporary designation and posts the candidate so other observatories can try to see it. This follow-up is crucial. Large telescopes can take deeper images, confirm the motion, and add fresh points to the orbit solution. Observers spread around the world help cover different time zones and weather, creating a continuous stream of measurements while the object is still bright enough to catch. At first, the orbit solution can fit many possibilities, including a normal solar system object. The numbers slowly narrow as more data arrives. If the best fit path is an open curve, a hyperbola, and the excess speed is too high for the object to be bound to the Sun, astronomers flag it as a likely interstellar visitor. The excess speed is measured at large distances where the Sun's pull is small. If the object is still going faster than the speed needed to escape, it did not start here. This conclusion does not depend on a single image, it depends on a chain of images that all agree with the same story. Parallax is another helpful clue. Because Earth rotates and observatories sit at different places on the planet, the object appears in slightly different positions against the background stars from one site to another. Combining these differences lets astronomers estimate distance more confidently. A nearby object shows more parallax, a distant one shows less. This helps separate a slow close object from a fast far one when their sky motions look similar over short timescales. Good parallax measurements require careful timekeeping, so observatories sync their clocks to standards like GPS to within fractions of a second. Brightness measurements are recorded along with position. If the object's brightness rises and falls in a repeating pattern over hours, that suggests it is rotating and not perfectly round. The pattern of bright and dim phases is called a light curve. Light curves help estimate the rotation period and hint at shape, like whether the object is elongated. Colour filters can also be used, taking images through different wavelengths to judge whether the surface reflects more red or blue light, which gives simple clues about composition. None of this requires a visible tail. Even tailless objects can be studied this way. False positives are common at the start. A satellite flare can mimic a moving point. A cosmic ray hitting the detector can draw a bright speck that appears in one image but not the next. To control this, Pipelines compare the same sky region with images taken seconds apart and reject anything that does not persist. They also keep mask maps of known satellite paths and bad pixels. Quality checks score each candidate on multiple tests. Shape looks like a point spread function, motion is consistent across exposures, brightness is steady or changing in a physically reasonable way, and the object is not too close to a known artifact or star halo. Survey cadence, the pattern of how often a patch of sky is revisited, is designed to balance discovery and follow-up. A common rhythm is take 4 short exposures of the same field within an hour, then move on, then return the next night. The spacing is chosen so a typical asteroid near Earth will move enough to be noticed, but not so fast that it streaks into a blur. Interstellar objects often have higher sky speeds and unusual directions compared to ordinary asteroids, so they stand out in the automated filters that expect solar system-like motions. That oddness score is one reason they get extra attention quickly. Weather, moonlight and season all matter. Thin clouds reduce sensitivity and can erase the faintest objects from a night's data. A bright moon increases the background light and hides the dimmest dots. In some seasons, a region of sky is too close to the sun to observe safely, so an object can be discovered late in its approach, leaving little time for study. Teams plan around these limits by coordinating multiple sites at different longitudes and latitudes, and by prioritizing follow-up when a high-interest candidate appears. Once a candidate looks convincing, additional techniques are used. Spectroscopy splits the object's light into many fine colors to search for signatures of ices or rocky minerals. Infrared imaging helps estimate size because warmer objects glow slightly at longer wavelengths. Combining reflected light, which depends on reflectivity, with thermal emission, which depends on size and temperature, reduces uncertainty. If the object releases gas, radio telescopes may detect molecules like carbon monoxide, providing direct evidence of activity. Each method adds a layer: where it is, how it moves, how it spins, what it's made of, and how it reacts to sunlight. Communication is simple but fast. Observers post their measurements in standardized formats, including the observatory code, time, coordinates, and uncertainties. Orbit-fitting software ingests the new points and recalculates the path, updating prediction charts that tell others where to look next hour and next night. If the object is faint and fading, these updates make the difference between catching it and losing it. Amateur astronomers with well-calibrated setups can contribute too. Precise timing and careful calibration can make small telescopes useful for light curves and astrometry, while large facilities chase spectra. The moment of recognition that this moving dot is not bound to our sun comes from the math being consistent across many nights and many telescopes. There is no dramatic sound or visual. There is a curve on a plot that stays open no matter how you test it, and a speed that remains too high to be explained by a standard long-period comet. With that, the community treats the object as a passerby from elsewhere and focuses on collecting the most informative data while it is still within reach. The process is routine in its steps and extraordinary in its result. A visitor from another star system quietly enters our data stream, identified not by a single breathtaking image, but by careful repeated measurements that agree with one another. All of this happens while most people sleep. Telescopes expose, servers hum, pipelines filter, alerts ping. By morning, a small set of coordinates and numbers tells a clear story. Something came into our sky that does not belong to it, and for a brief time we can watch, measure and learn before it slips back into the dark beyond our sun's influence. The space between stars is not empty. It is just very, very thin. A teaspoon of air on Earth holds more particles than a cube the size of a house out there. Yet across that thinness, a small natural body can travel for ages. Picture a cold object, part rock, part ice, or something in between, moving because long ago something pushed or threw it out of its home system. That push could have been a near pass by a giant planet, a close brush with another small body, or the slow tug of many small pulls over time. Once free, it did not stop. In space, there is almost nothing to slow you down, so momentum becomes a kind of promise. If nothing strong acts on you, you keep going in the same direction at the same speed. Temperature in deep space is not a number you feel on your skin. It is about how much energy an object absorbs and gives off. Far from any star, sunlight is weak, so the surface settles toward very low temperatures, tens of degrees above absolute zero. If the object spins, one side warms a little under the distant light while the other side cools. That difference smooths out as heat conducts inward and outward. Over hours and days and years, the object cycles through tiny warm-ups and cool-downs. These changes are small, but over long periods they can cause surface layers to crack or crumble, a process called thermal fatigue. Grains loosen, dust forms, and the topmost skin becomes a kind of weathered shell. Radiation is another quiet sculptor. High-energy particles from stars and from the galaxy, cosmic rays, hit the surface, breaking chemical bonds and darkening ices. This space weathering can change how reflective the object looks. Fresh ice is bright. Processed ice can turn dull and grey-brown. If the object carries organic molecules, radiation can rearrange them into more complex mixes. This does not make the object living, it simply changes the chemistry. Over millions of years, a thin crust may grow that traps fragile ices underneath, like a rind on frozen fruit. When such a crust is later warmed near a star, gas can find weak spots and vent, lifting dust into a short-lived coma. The journey is guided mainly by gravity. On the larger scale, the galaxy's mass sets the background. On smaller scales, passing stars add little nudges. Most of the time, those nudges are tiny because distances are enormous. But every so often, a star drifts close enough that its gravity changes the traveller's path by a fraction of a degree. It does not feel like a turn. It is more like a slow, inexorable bending that only shows up when you compare the path over millions of years. The combined effect of thousands of distant tugs, plus the very weak galactic tide that pulls on everything in the Milky Way, is to give the traveller a path that is not perfectly straight on the grandest maps, though it is close enough to straight for our local view. Spin is part of the story as well. Most small bodies are not perfect spheres, and their spin states can be complicated. Some tumble, rotating around more than one axis like a dropped book that flips and wobbles. In starlight, even a very small push called radiation pressure can, over long times, subtly alter spin or orientation. For objects within a stellar system, there is a known effect, the YORP effect, where uneven heating and re-radiation of heat can torque a body. In true interstellar space, far from strong sunlight, these effects are much weaker, but they never quite go to zero. The result is a traveller whose spin may wander slowly across centuries, never settling for good, always responding to small, persistent forces. Micrometeoroids, dust grains and tiny fragments, sometimes hit the surface. Each impact is a micro-explosion at the scale of grains. It sputters atoms away, chips small pits, and lifts clouds of even finer dust that might escape or resettle nearby. Over long times, this sandblasting rounds sharp edges and softens features. If the traveller once had crisp fractures or fresh frost, they can blur into smoother slopes. This gradual smoothing does not erase the whole history. It just layers new textures over old ones, like wind rounding the corners of a stone. Mass can change during the crossing. Out in the dark, most ices are stable. They do not evaporate quickly when the heat source is distant. But some super volatile ices, like carbon monoxide or nitrogen, can slowly leak even in weak sunlight. That leak is tiny, yet it runs for a very long time, so a thin outer layer may be lost across eons. If the body rotates, any asymmetric venting acts like a small thruster and can slightly adjust the spin or path. The changes are minute, but they accumulate. Think of it as a long arithmetic sum where each term is small, the total can still be noticeable. Timescales are the most difficult part to grasp because they are so large. A traveller could spend tens of millions of years between stars and still be recent by galactic standards. It might cross regions of the interstellar medium with different densities, a warm, low-density bubble here, a cooler, slightly denser cloud there. Those differences change the rate of particle impacts and the character of the radiation environment. They can also alter how electric charges build up on the surface and how dust clings or drifts away. None of this is dramatic moment to moment, but the ledger of small effects keeps filling line by line. The object's shape affects its thermal life. Elongated bodies flip more unevenly between day and night sides, creating larger temperature swings at ends or ridges. Deep cracks act as shadows that trap cold for longer, making some pockets more stable for ices. A porous interior slows heat flow, protecting deeper layers from surface changes. If there are voids, they can collapse under tiny vibrations from impacts, subtly changing the mass distribution. The physics is simple: conduction, radiation, rotation. But the geometry turns that simple physics into rich patterns that make each traveller unique. If the object began in a young planetary system, its ejection likely came from encounters with big planets. In such systems, giant planets stir small bodies and throw some outward at high speed. Those that cross the outer boundary gain enough energy to leave the star for good. That first phase is violent compared to the long crossing that follows. Once free, the traveller enters a quiet mode. It no longer experiences close, disruptive meetings unless chance brings it near another star. In this quiet mode, the key currency is exposure. How long has it been out there? How much radiation has it absorbed? How often has it passed near a star close enough to warm it above the deep cold baseline? Colour, brightness, and reflectivity change little by little. A once brighter surface can darken. A rough surface can become more matte. If and when the object later enters a new star's outer regions, like the outskirts of our solar system, these altered surface properties affect what we see. A darker object warms slightly more in sunlight. A brighter one reflects more and stays cooler. These differences change how much gas, if any, is sucked up when warmed. So the long cold crossing does not erase identity. It prepares the surface to respond in a particular way when starlight finally rises again. Magnetic fields in space are weak but are widespread. Charged particles spiral along them. If the traveller slowly accumulates charge on its surface, electric forces can lift and transport dust grains in tiny hops. On airless worlds like the Moon, such effects are seen near the day-night boundary. Grains can levitate briefly. For a small interstellar body, the same physics, scaled down and slowed, could help rearrange fine dust into smoother blankets, or expose small patches of harder crust. Again, the changes are not dramatic. They are quiet edits written in small print. Mass distribution matters for stability. A lopsided body can be more prone to chaotic tumbling, while a more symmetric one tends to settle into a stable spin, although small torques can always disturb it. If cracks divide the interior into weakly connected blocks, even a modest temperature change over many cycles can shift those blocks, making the spin wobble. Think of this as internal weather, slow, silent activity that changes the way the object presents itself to light and to our telescopes later on. Navigation through the galaxy is blind. The traveller does not steer. It simply follows the path that gravity and initial speed laid out. Yet we can still talk about routes because stars are not evenly spread and clouds of gas are not uniform. In some regions, the traveller is more likely to be perturbed. In others, it cruises with fewer interruptions. Over 100 million years, the Milky Way itself turns, and the traveller with it, so its surroundings change even if its local speed stays the same. That is one reason two interstellar visitors can look and behave very differently. They come from different histories written by different neighbourhoods. When such a body drifts into a new star's influence, the first signs are subtle. A tiny bend in its otherwise straight track, a slight increase in sunlight, a small change in surface temperature. If ices lie just under a thin crust, The earliest warming can build pressure until a microvent opens. A puff of gas escapes carrying dust. If vents are patchy, the gas jets are patchy too, and the jets apply small pushes that can speed up or slow down rotation. A body that was tumbling slowly can begin to wobble more noticeably. To an observer with a telescope, these internal adjustments appear as changes in brightness and colour over hours and days. Still, most of the crossing is a lesson in patience. No engines fire, no maps are read. The only tools at work are the steady rules of physics and the enormous length of time available for those rules to leave a mark. The traveller's surface becomes a record of exposure. Its spin becomes a record of torques. Its path becomes a record of distant, gentle pulls. By the time it wanders into our sky, it carries a history written in low contrast, a palimpsest of darkened ice, softened edges, and a rotation pattern that makes sense if you know how to listen. Our measurements, light curves, colours, spectra, are ways of listening, translating that long, cold crossing into numbers we can compare and understand. For anyone trying to picture what that crossing feels like, think quiet repetition. Day-night cycles stretch thin by distance from any star, impacts so rare that years can pass without a single notable one, temperature changes that would barely register on a household thermometer, but that matter when repeated millions of times. It is the kind of environment where even the smallest effect earns a result simply by persisting. And it is why, when the traveller finally reaches the edge of a solar system like ours, the response we observe is not random. It is the natural outcome of a body prepared by deep time to react in certain ways to rising light, to gentle warmth, and to the curved pull of a new sun. Names and numbers are how astronomers keep a crowded sky organised, and they are meant to be read like labels on a toolbox. Start with the big idea. Every new object gets a temporary tag the moment it is noticed, then a more official name once its path is confirmed, and sometimes a special label if it belongs to a rare group. For interstellar visitors, the special label looks like 1i/... 2i/... 3i/... The I stands for interstellar, and the number counts the discovery order. So 3i Atlas means the third interstellar object ever recognised, first reported by the Atlas survey. Atlas itself is a Skywatch program whose name is short for Asteroid Terrestrial Impact Last Alert System, a set of robotic telescopes that take wide, frequent pictures to catch moving dots. The survey name after the slash tells you who first raised the flag, the way a news article credits the first reporter on the scene. Before an object earns a clean 3i label, it almost always appears with a provisional designation that encodes when it was found. For ordinary asteroids, the format looks like 2025 AB or 2025 AB1, where the year is clear, the letters map to the half-month and the sequence within that half-month, and the small number is a tiebreaker when we run through the alphabet a lot. Comets start with letters that tell you their type. C/ for a long period or non-periodic comet, not known to return on a short schedule. P/ for a short period comet, known to return on a short schedule. A periodic comet, roughly under 200-year returns. D/ for a comet that has broken up or is lost. And X/ for a comet recorded in the past with too little data for a reliable orbit. When it became clear that some visitors are not bound to the Sun at all, the community agreed on I/ to mark that category, with a simple number that increments as new cases are confirmed. Once the basic label is set, the next important things are a handful of numbers that describe the path and the brightness. Path numbers are called orbital elements. You will often see the eccentricity E, the inclination AA, the perihelion distance Q, the longitude of the ascending node omega, the argument of perihelion omega, and the time of perihelion TP. If that looks like alphabet soup, here is the plain version. Eccentricity tells you how stretched the path is. Circles have E equals 0, stretched ellipses have 0 less than E less than 1, and open one-pass paths have E greater than 1. Interstellar objects show E comfortably larger than 1, which is the mathematical way to say they are on a get in, pass by, get out track. Inclination is the tilt of that track compared to the flat plane where most planets orbit. An inclination near 0 degrees means it is near that plane. 90 degrees means it dives straight over the top, and anything in between tells you the slant. Perihelion distance is how close the object will get to the Sun, measured in astronomical units. 1 AU is the average distance from Earth to the Sun. The 3 Greek letter angles, omega, omega, and the time TP, are the where and when details that let a computer draw the curve in the right part of the sky at the right moment. Brightness gets its own simple but slightly tricky number called absolute magnitude, written H for asteroids and a similar H with an activity slope for comets. H is how bright would this object look if we placed it at a standard distance, which lets us compare fair and square between near and far. Smaller h means brighter, larger h means dimmer. To turn brightness into size, you also need albedo, which is the fraction of sunlight the surface reflects. A shiny object, high albedo, can be small and still look bright. A dark object, low albedo, can be large and still look dim. If albedo is unknown, astronomers give a size range. If it is dark, it is about this big. If it is brighter, it's about that big. Because interstellar visitors are new to us and usually faint, that range can be wide at first and then narrows as more data arrives. Another everyday number in summaries is the speed v infinity. Read v infinity. It is the speed the object would have far from the Sun, where the Sun's pull is practically 0. For interstellar bodies, v infinity is positive and not tiny, which means they were already cruising before they arrived and will keep cruising after they leave. You may also see A, the semi-major axis, which is negative for a truly open hyperbolic path. That negative sign is a compact way the math uses to say this orbit does not close. For safety watchers, a value called MOID, minimum orbit intersection distance, appears too. It estimates the closest possible distance between the object's path and Earth's path. A large MOID means no concern. A very small MOID means careful attention, even if in practice timing still keeps the actual object far away. Light curves, plots of brightness over time, produce a rotation period p and an amplitude delta. MP tells how long one spin takes. Delta M tells how uneven the shape or surface is. A big swing in brightness often means the object is elongated, like a potato showing a larger and then a smaller side as it turns. Colours measured with filters, for example G-R or R-I, which compare brightness through slightly different green, red or infrared windows, hint at surface materials. Redder colours can suggest certain processed organics or dusty coatings. More neutral colours can suggest fresher ice or rock. These are clues, not final verdicts, but they help teams decide what kind of deep observations are worth trying next. Where do all these names and numbers live? They're collected by central services so everyone can talk about the same thing. Observers send in astrometry, precise positions and times, and photometry, brightnesses and filters, in a standard format that includes the observatory code, the timestamp, the measured coordinates, and an estimate of uncertainty. The data aggregator checks for mistakes, posts the observations, and assigns or updates the designation. Orbit fitting software ingests all reported points, calculates best fit elements and their uncertainties, and provides prediction tables so others know where to look tomorrow and next week. As fresh points arrive, the solution is recomputed, the uncertainties shrink, and the predicted path tightens like a camera bringing a subject into focus. Uncertainty is part of the label set, and it is honest about what we do not yet know. You might see a single-digit U parameter for older asteroid solutions or explicit error bars for modern solutions. A small uncertainty means many good measurements scattered over many nights. A large uncertainty means we have only a short arc or noisy data. For fast, faint visitors, the early numbers carry bigger error bars, which is normal. This is also why naming has stages. A provisional tag first, then a formal interstellar label when the case is strong, and sometimes a friendly public-facing name after that. Public names can honour discoverers, places, cultures, or ideas, but they must follow community rules that avoid confusion and duplicates, and they never replace the compact code scientists use in calculations. It helps to know a few survey names you will see often. Atlas is the one in our title, and its job is frequent, wide-field watching to catch fast movers. Pan-STARRS is another wide-field program well known for discovering small bodies and near-Earth objects. ZTF, Zwicky Transient Facility, is designed to find changing or moving things quickly across huge sky areas. Professional surveys use sensitive cameras, careful calibration, and well-tested software so that when a dot is flagged, its numbers mean something. Amateur observers and small observatories join the story too. With accurate timing and good calibration, they can add light curves and extra astrometric points that sharpen the orbit. Pronunciation and writing details sometimes appear in summaries because names travel across languages. For example, the first interstellar object, 1I/Oumuamua, included an okina, a glottal stop, in Hawaiian. Guides explained how to say it and why that mark mattered. The point is not fussiness. It is respect for where names come from, and clarity when many people around the world are discussing the same object. In our case, ATLAS is easy to say, and reminds you which system first spotted the visitor. When you look at a fact sheet or a database page for a new object, a quick way to read it is to scan for 5 items: the designation, what it is and who found it, the status, provisional, confirmed, interstellar label applied, the orbit type, look at E and whether the solution calls it hyperbolic, the size estimate, H with an assumed albedo range, and any behaviour notes, coma detected, tails seen, rotation period measured. Those 5 tell a clear story at a glance. If you want depth, you can dive into the residuals, how well the orbit matches each observation, the covariance matrix, how the errors in one element relate to errors in another, and the list of contributing observatories to see how global the coverage has been. Finally, the reason to care about names and numbers is that they let everyone coordinate. A short code in an alert message is enough for a telescope scheduler to place a target on a cue before dawn. A clean set of elements lets a classroom planetarium app draw the path for students the next day. A clear absolute magnitude with a stated albedo lets a science communicator give a responsible size range on a live stream. Without the shared labels, every team would be talking past the others. With them, a faint smudge becomes a well-defined entry in a living catalogue, and the catalogue becomes a map of what we have learned so far. The name tells you the lineage, the numbers tell you the motion and the nature. Together, they turn a one-line discovery notice into something the whole community can build on, update, and understand at a glance. Measuring a fast faint visitor is a step-by-step process that turns tiny bits of light into useful facts. The first job is to nail down where it is and how it moves. Telescopes take short exposures and record the exact time for each image. Software matches background stars to a catalogue and corrects for small distortion so every pixel maps to a precise sky coordinate. The moving dot is then fit with a point spread function to get its centre. That position, with an uncertainty in arc seconds and a timestamp to fractions of a second, is astrometry. Astrometry from many sites and nights feeds an orbit solver that returns the path and its error bars. If the object trails during an exposure because it is fast, we either shorten the exposure or track the telescope at the object's rate so the dot stays compact and the position remains accurate. This is how we keep the path prediction tight enough for everyone to find it on the next night. At the same time, we ask how bright it is and how that brightness changes. This is photometry. Each image is calibrated with bias, dark and flat field frames, so the camera's quirks do not masquerade as real signals. We measure the object's counts within a small aperture and subtract the local sky background. Then we convert counts to magnitudes using nearby standard stars with known brightness in the same filter system. Because Earth's atmosphere dims light more at low elevations, we apply an air mass correction derived from comparison stars across the frame. The result is a calibrated magnitude with an uncertainty based on photon noise and calibration scatter. Repeating this in filters like G, R, I, or VRI gives colours that hint at surface composition or dust in a coma. Brightness versus time reveals spin. If the object is elongated or has bright and dark patches, it will get brighter and fainter as it rotates. We collect a long sequence of measurements and run a Lomsgardle preodogram or similar tool to find repeating patterns. The period tells us how long one spin takes. The amplitude tells us how stretched or irregular it may be. A large amplitude often points to a very elongated body. A small amplitude suggests a more rounded shape or a view looking near the spin pole. If activity adds a faint coma, it can dilute the amplitude. In that case, we use smaller apertures or model and subtract the coma to recover the nucleus signal. The way brightness depends on the Sun-object-Earth angle, the phase angle, is also informative. Airless surfaces typically follow a predictable phase curve. As the phase angle shrinks towards zero, many bodies show an opposition surge, a gentle brightening caused by shadow hiding and coherent backscatter. We fit simple phase curve models like HG or HG1, G2 systems for asteroids to estimate the absolute magnitude h, which is the brightness standardized to a fixed distance and zero phase. To turn h into a size estimate, we assume a reflectivity albedo. A dark surface means a larger size for the same h. A shiny surface means a smaller size. Thermal infrared data, when available, breaks this degeneracy by measuring the heat glow and letting us solve for both size and albedo with a simple thermal model like NEATM. Colour and spectra go deeper. Low-resolution reflectance spectra, sunlight reflected off the surface divided by a solar analog star, show gentle slopes and broad features that distinguish ice-rich, rock-rich or organics-rich surfaces. A red slope can indicate space-weathered organics and dust. A neutral or slightly blue slope can indicate fresher ices or certain minerals. If activity is present, gas emission lines can appear. For comets, these include CN, C2 or CO bands. Measuring their strengths allows rough gas production rates using standard coma models. In very faint cases we cannot detect lines, but we can set meaningful upper limits that still constrain what the object is doing. Polarimetry adds another piece. By measuring how the reflected light is polarized at different phase angles, we probe grain sizes and surface texture. Many airless bodies show a characteristic polarization curve that crosses zero at a small phase angle. The depth and position of the negative polarization branch relates statistically to albedo. Even a few high-quality polarimetric points can nudge our size and surface estimates in the right direction. When the object is extremely faint or moving fast, we use advanced tricks to boost signal without losing accuracy. Shift and stack, or synthetic tracking, aligns and coadds multiple short exposures along the predicted motion, so the object adds up while background stars blur. This increases the signal-to-noise ratio by roughly the square root of the number of frames, letting us extend light curves and colour measurements to fainter levels. Because wrong rates smear the target, we search a small grid of rates near the prediction and pick the stack that yields the sharpest peak. Every stack still gets calibrated photometrically, so the magnitudes remain on a standard system. Activity is checked carefully. We compare the object's radial profile to field stars of the same brightness. An excess width or a slight halo indicates a coma. If present, we can estimate dust production using AFRHO, a simple quantity that scales with the dust cross-section in the aperture. Repeating AFR over time shows whether activity is rising or fading as the object approaches or recedes from the sun. We also inspect deep stacks for any tail aligned with the antisolar direction or the velocity vector. Even a short, faint tail can confirm outgassing and help explain non-gravitational forces that slightly tweak the orbit. Non-gravitational accelerations are measured by fitting small extra terms to the orbit solution, often labelled A1, A2, a 3 and a cometary model, to capture gentle pushes from asymmetric outgassing. If including these terms reduces residuals significantly and consistently, we keep them. If not, we avoid overfitting. Detecting a tiny steady acceleration can explain why a purely gravitational fit drifts over weeks. Light curve changes can support the same story by showing spin state evolution caused by jets acting like thrusters. Coordinating many telescopes keeps the coverage smooth. Small telescopes collect dense light curves and astrometry in bright windows. Larger facilities chase spectra and polarimetry when the object is highest in the sky. Observers share ephemerides with uncertainties, recommended exposure times, and rate tracking settings so others can reproduce results. Time standards are synchronized with GPS or network time to avoid millisecond-level errors that would matter for very fast targets. Every team reports their site code, filter set, and reduction pipeline details, so measurements from different places can be combined without hidden biases. Data quality control never stops. We examine residuals from the orbit fit to catch bad points or timing mistakes. We check color terms and 0 points by comparing to published standard star sequences in the field. We propagate uncertainties correctly. Photon noise, calibration error, sky background variance, and trailing losses all contribute. When a result depends on a model, thermal size, gas production, we clearly state the assumed parameters so later teams can update numbers if better inputs appear. In parallel, we publish upper limits when we see nothing. Strong non-detections are valuable, drawing lines around what the object cannot be doing. Special opportunities sometimes occur. If the path crosses in front of a star as seen from a narrow strip on Earth, an occultation can reveal the silhouette, giving a direct size and even hints of shape or a surrounding dust envelope. Predicting such events requires precise astrometry and quick sharing. Observing them requires portable setups and coordination across the path. A successful chord measurement from even 2 stations can beat indirect size estimates by a wide margin. Although rare for fast interstellar visitors, we prepare in case geometry lines up. All the while, we keep the observing plan practical. We prioritize phase angle diversity for phase curves, long continuous sequences for rotation, multi-filter pairs close in time for color, and a few deeper visits for spectra and polarimetry. We adjust cadence as the object brightens toward perihelion and fades afterward, balancing exposure time against trailing. We retire filters that add little and focus on the bands that maximize information per minute under the current sky conditions. When the moon is bright, we favor redder filters that suffer less background. When seeing is sharp, we use smaller apertures to improve signal to noise. By combining positions, brightness, échantillons, colors, spectra, polarization, and, when lucky, thermal data or occultations, we turn a faint moving point into a physical sketch. An object with a likely size range, a spin period and light curve amplitude, a surface reflectivity and color class, a degree of activity or its absence, and an orbit with quantified uncertainties and any small non-gravitational pushes. Each technique checks the others. If the thermal size disagrees with the photometric size and any reasonable albedo, we re-examine calibrations. If the light curve period conflicts between nights, we test for tumbling by fitting 2 frequencies. If the orbit drifts, we explore whether weak jets or systematic timing errors are to blame. The payoff is a coherent picture built from many small, careful measurements that remain understandable, even as the visitor dims and slips beyond the reach of our telescopes. Interstellar visitors are like sample return missions we didn't have to launch, and even when we can't touch them, the light they reflect and the way they move act as lab reports about other solar systems. The first and clearest lesson is about how planets form. Every small body is a leftover from a construction site, a piece of the original building material that did not become a planet. By comparing an interstellar object's brightness, colour, and activity with the comets and asteroids born around our Sun, we test whether the recipe for building worlds is similar everywhere or highly local. If many visitors look icy, for example, that supports the idea that young planetary systems commonly make wide belts of frozen debris beyond their giant planets. If some arrive looking dry and rock-like, that hints at strong heating or different mixing of materials in their birth disks. Over time, a catalogue of colours and behaviours becomes a map of chemical gradients in other systems, telling us where water and carbon-rich ices tend to collect and where rock dominates. Composition is the second lesson, and we can read it in several ways. The simplest clues come from colours measured through different filters. Red slopes can indicate dusty, organic-coated surfaces. Neutral or slightly blue slopes can point to fresher ice or certain minerals. If a coma forms, spectra may show gas fingerprints, bands from molecules like CN or C2 in the visible, or carbon monoxide and water in infrared and radio, each one a clue to what lies just under the surface. Even non-detections matter. If we see no typical gas lines at a distance where ordinary comets would already be venting, then either the visitor's ices are buried deeper under a processed crust, or its mixture is genuinely different. When thermal infrared measurements are possible, they help separate size from reflectivity. A bright small object and a dark larger object can look equally bright in visible light, so the heat glow breaks the tie and tightens our estimates, which then feed back into composition models. Activity physics is a third lesson. Watching when and how a visitor turns on teaches us about porosity, layering, and the strength of the crust. Many comets vent gas smoothly as they warm. Others stay quiet and then open sudden jets when pressure breaks through sealed pockets. The timing of that switch on compared to its distance from the sun tells us how easily sunlight penetrates and how well the surface traps volatiles. If a visitor shows outgassing at unusually large distances, that suggests super volatile ices like CO or N2 that sublimate in weaker sunlight. If it waits until it is close, water ice may dominate under a tougher skin. The tiny pushes from jets also show up as non-gravitational accelerations in the orbit fit, giving a backdoor way to measure how much thrust the vents provide and how the object's mass and shape respond. Put together, these effects reveal whether we're looking at a rigid monolith, a loosely bound rubble pile, or something in between. Spin and shape offer a fourth lesson about the stresses small bodies survive. A strong, coherent object can spin faster without breaking. A fragile, fluffy body cannot. By measuring the rotation period and the change in brightness over each spin, we get a handle on elongation and internal strength. Large amplitude light curves often mean a long, thin shape or a contact binary. Low amplitudes may mean a more rounded body or a view near the spin pole. If the period changes over weeks, sunlight-driven torques or jetting are modifying the spin, which in turn hints at surface roughness and mass distribution. Across many visitors, statistics of spin and amplitude will tell us how often other systems produce shards, aggregates, or gently fused peanut shapes, and whether the interstellar environment smooths or fractures them over time. Surface processing is a fifth lesson, written by radiation and tiny impacts during the long cold crossing between stars. Space weathering can darken and redden ices and organics. Micrometeoroid hits can sandblast edges and create fine dust that settles into pores. When we compare a visitor's reflectivity and colour to models of weathering timescales, we infer how long it has been exposed and whether it has been refreshed recently by a split, a landslide, or a past close pass to a star. If a visitor looks surprisingly fresh, it might have been ejected not long ago from a young system. If it looks heavily processed, it may be older, or have drifted a long time through harsher radiation fields. In this way, a spectrum becomes a rough clock. Dynamical lessons come from the path itself. The incoming speed far from the sun has the V infinity, and the direction in the sky act like a return address, not precise enough to name a specific star, but good enough to say how typical or unusual the trajectory is. If we find many arrivals clustered around the local standard of rest, random drift dominates. If we see groups arriving from preferred directions, Nearby moving groups of stars or recent star-forming regions could be seeding space with debris. The sheer rate of discoveries, once surveys are uniform, constrains how efficient young planetary systems are at ejecting leftovers. High rates imply that growing giant planets commonly sling small bodies outward. Lower rates suggest more debris stays home or grinds down before ejection. These numbers feed planet formation models, sharpening our understanding of how and when giant planets migrate, and how that migration shakes loose vast belts of rock and ice. Organic chemistry provides another area of insight. Comet-like bodies often carry complex carbon compounds formed in cold conditions by radiation processing of simple ices. If we detect signatures of these compounds, even broadly, it supports the idea that organic chemistry is widespread and robust in planetary nurseries. If we do not, or if we see different mixtures than in our comets, that points to diverse chemical histories, perhaps different UV fields around their stars, different dust-to-gas ratios in their disks, or different timelines for heating events. None of this claims life. It simply measures the inventory of prebiotic ingredients that star systems tend to cook up before planets finish forming. Thermal properties add a practical lesson with broad implications. An object's ability to absorb and re-radiate heat, the thermal inertia, controls how quickly it responds to sunlight. Low thermal inertia implies a fluffy insulating surface. High thermal inertia implies denser or rockier material. By fitting how the brightness and any thermal signal change with phase angle and distance, we estimate this property, and thus get indirect evidence for grain size and packing. This matters not only for understanding the visitor itself, but also for predicting how similar bodies would behave if they entered our neighbourhood again, including how bright they might get and how quickly their activity would evolve. Size distribution is a population-level lesson we can reach even when single objects remain fuzzy points. If surveys can detect visitors down to a certain brightness and we count how many appear each year, we can infer how common small, medium, and large interstellar fragments are. A distribution rich in small bodies means collisions and grinding are frequent in young systems. A distribution that includes some very large pieces means either gentler histories or occasional catastrophic events that throw out big chunks. This distribution also feeds estimates of the total mass that stellar systems leak into the galaxy over time, contributing to a picture of how material cycles between stars and the spaces between them. Delivery of volatiles to planets is a quietly important lesson that interstellar visitors help calibrate. In our own system, comets and certain asteroids likely delivered water and organic materials to early Earth. If visitors are common and icy, then cross-system delivery, rare on any one world but non-zero over long times, could be a background process in the galaxy, sprinkling outer system ices inward when stars pass near each other, or when planetary systems evolve in crowded birth clusters. Observing the volatile budgets of visitors allows us to bound how much such delivery could matter without invoking speculation. This frames careful, testable discussions about habitability that rest on measured inventories rather than wishful thinking. Even the lack of a tail can teach us. A visitor that stays star-like and shows no coma, even when it should be warm enough to vent if water ice were near the surface, hints at either a thick crust that seals in volatiles or a composition poor in ices altogether. That in turn points to ejection from drier, inner regions of a system or strong early heating. If we later catch a brief localized outburst, the contrast tells us about patchiness, reservoirs isolated under a tough rind that open only when stress lines connect to the surface. These patterns give engineers and mission planners realistic expectations about what a future flyby or sample attempt might encounter. Polarimetry, though technical, adds a grain-size lesson with surprising leverage. The way reflected light becomes polarized depends on the roughness and porosity of the topmost layer. When we put a visitor's polarization curve next to the curves of our comets and asteroids, similarities and differences jump out, letting us refine grain-size distributions and albedo estimates without touching a grain. This cross-check reduces ambiguity in size. boosts confidence in composition hints, and helps us see whether interstellar surfaces are dustier, fluffier, or crustier than the surfaces we know best. Occultations, when a visitor briefly blocks a star, offer silhouette lessons that can trump indirect estimates. A clean, flat-bottomed dip in starlight timed by even a couple of stations can give a true chord across the object, a direct size measurement independent of reflectivity. If multiple chords are captured, we learn shape and can detect a surrounding dust envelope, just from how the star fades and rebrightens. While rare for fast movers, even one success would anchor the scale of a visitor and calibrate thermal and photometric models used for others, raising the quality of every derived number that depends on size. Finally, each observation of a visitor improves our tools. Pipelines for difference imaging get better at rejecting false alarms. Orbit solvers become more robust at handling very high speeds and weak non-gravitational forces. Scheduling software learns to prioritize targets that fade quickly. These upgrades loop back into broader sky safety because the same systems watch for near-Earth asteroids. In that sense, interstellar objects teach us twice. They teach us about other planetary systems directly, and they make us better at reading our own sky. With every visitor, the list of lessons grows: materials, temperatures, spins, shapes, activity thresholds, chemical inventories, ejection rates, background delivery possibilities, and the hard limits on what is not happening. And those lessons, stacked patiently, turn a handful of faint wanderers into a reliable, testable understanding of how worlds are made and how pieces of them travel between the stars. Gravity is the quiet sculptor of every path an interstellar visitor takes, and its work begins long before the object reaches our sky. Far from any star where the pull from individual suns is weak, the combined mass of the galaxy sets a broad stage. That background field is like a slow, steady slope that everything rolls across, guiding the traveller along a nearly straight line compared to the huge scale of the Milky Way. On top of that background, passing stars add tiny bends. Most of the time, those bends are so small that only a computer can notice them over millions of years, but they matter because gravity never turns off. It acts constantly, adding up its influence grain by grain until the line you thought was straight is, in fact, a graceful arc set by every mass nearby. As the visitor drifts into our solar system's outskirts, the sun's pull takes charge. A useful way to picture this is the sphere of influence, a bubble around a body within which its gravity dominates guidance. The sun's bubble is enormous. Each planet has a smaller bubble inside it. When the traveller is in the sun's domain, its path is well described by a conic section, a Keplerian curve set by gravity alone. If the eccentricity of that curve is greater than 1, the track is hyperbolic, meaning the object arrives from infinity, swings by and departs back toward infinity. It is not captured, it is escorted. The sun's gravity acts like a lens, bending the track inward as the object falls, speeding it up as it approaches perihelion, and then letting it climb away with the same energy it had when it came in, minus or plus any changes from other influences encountered along the way. Planets add the gentle filigree on this solar bend. Each planet carries a smaller, moving bubble of dominance, the region inside which the planet's gravity is stronger than the sun's for a passing body. When the visitor crosses that region, the problem becomes a three-body dance: sun, planet, and traveller. Even if the traveller never gets close to the planet's surface, a distant pass can exchange a little energy and momentum. To visualise this, imagine a river current, the sun's pull, and a slow swivelling eddy, the planet's pull, rotating around the river's centre. Drift through the edge of the eddy, and your direction changes by a few degrees. This is the essence of a gravity assist, or gravitational scattering. To the traveller, it is just a smooth turn. To us, it is a precise, predictable nudge that can adjust the outgoing speed and direction by just enough to matter for where we see it next night and next week. Because planets move, timing decides everything. If the visitor slips behind a planet's motion, it can steal a little orbital energy and leave with a slightly higher heliocentric speed. If it passes in front, it can give energy back and leave a little slower. These changes are small for distant passes and remain small unless geometry aligns just right. Most interstellar visitors never thread the narrow keyhole needed for large planetary kicks, but even small angle changes can shift the skytrack by many moon widths over days. That is why observers update ephemerides frequently, accommodate the sun's big bend and then trim the predicted line for any planetary nudges that fresh measurements reveal. The sun's pull also couples to the visitor's speed in a way that shapes what we see without any collisions. As the object falls inward, it accelerates. At perihelion, it is at its fastest, and when it climbs back out, it decelerates again. This accelerates and decelerates the apparent motion across our sky, changing how long we can collect deep exposures before trailing becomes a problem. It also modulates the brightness through distance, closer to the sun and Earth. More sunlight is available to reflect toward us, and less space dims the beam before it reaches the detector. All of that is gravity's doing, expressed through simple inverse square laws that set the rhythm of approach and retreat. Tides are gravity's way of noticing size. The sun pulls harder on the near side of a body than on the far side. A planet does the same during close passes. Most of the time, these differences are tiny compared to the strength of the object itself. But if the visitor is a loose aggregate, a rubble pile held together mostly by self-gravity and friction, then a close planetary pass can stir it. Blocks can shift, weak seams can open, and dust can be lofted if rotation and tides align. At truly close ranges, tidal forces can even fragment a body, as seen with comets that venture too near large planets in our own system. For a typical interstellar traveller, safe distances prevail and tides mainly act as invisible inspectors, probing the internal cohesion without leaving dramatic marks. Yet the possibility of subtle restructuring remains whenever geometry compresses. Resonances represent gravity's talent for order. In our planetary system, orbital periods lock into simple ratios, 2:1, 3:2, and so on, producing zones where repeated tugs line up and amplify over time. A quick passerby does not settle into resonance, but if it lingers near a commensurate motion with a planet during its brief stay, a sequence of aligned micropulls can add a touch more bend than a random pass would give. This is less a mechanism to reshape an interstellar trajectory and more a reminder that gravity prefers patterns. Even weak influences can accumulate when rhythm matches rhythm, and the skytrack bears those subtle fingerprints. Patchwork models help us compute all this cleanly. Far from a planet, treat the problem as a two-body sun traveller system and draw the elegant hyperbola. Inside a planet's sphere of influence, switch to a planet traveller two-body picture and connect the curves at the boundaries. This patched conics approach, used for decades in spacecraft navigation, is a faithful first approximation for natural bodies too. When we need more precision, we turn to full three-body or in-body integrations that step the equations forward in small time slices, letting the sun and all relevant planets pull simultaneously. The result is a path that looks simple in a planet's frame, a swoop past, a change in asymptote, and looks like a gently trimmed hyperbola in the sun's frame. There is a deeper language for these movements, framed by the constants of motion and energy surfaces. In a simplified three-body setup where a planet orbits the sun in a circle, the Jacobi integral behaves like a budget that combines kinetic and potential energy in a rotating frame. Level sets of this budget carve out forbidden and allowed regions of space. The traveller's pass near a planet can move it from one allowed lobe to another, changing which corridors through the solar system are accessible without ever firing an engine. Space mission designers use this insight to hop between regions via low-energy, invariant manifolds, tubes in phase space that act like gravitational highways. A natural interstellar object cannot aim for these tubes, but if its incoming state happens to line up, gravity alone can route it through surprisingly curved corridors with only the slightest planetary touch. While gravity dominates, softer forces ride along. Sunlight pushes on dust and very small bodies. The pressure of light scales with area, while gravity scales with mass. so smaller, fluffier fragments feel proportionally more push. Engineers package this as a number called beta. Beta near 0 means gravity rules. Beta approaching 1 means radiation pressure rivals solar gravity. For typical multi-tens of meters visitors, beta is effectively 0, yet any dust lifted from their surfaces can fan into tails that point away from the sun, and those dust grains then travel curved paths set by the sum of gravity and light pressure. From a distance, we see both stories at once, the nucleus following a gravity-bent hyperbola, and dust tracing lighter, more open curves that subtly diverge. If gas jets switch on, their thrust looks, in the orbit calculations, like a small acceleration aligned roughly with the sun object line or with the velocity. We model these as non-gravitational terms, but gravity still sets the stage on which they act. A tiny push delivered when the sun's gravity is already turning the path can lead to a slightly different outgoing aim, like tapping a steering wheel while rounding a curve. The effect is measurable as a slow drift between a purely gravitational ephemeris and the real sky positions. Correcting for it brings the predicted track back into alignment, and once corrected, we can separate the part due to gravity from the part due to venting. Close approaches highlight a comforting rule: risk falls off fast with distance. The gravitational deflection angle during a planetary pass scales roughly as the inverse of the impact parameter squared for fast movers, so doubling the miss distance cuts the bend to a quarter. Most interstellar visitors miss every planet by ranges measured in millions of kilometers, which means their bends are modest, fully modelled, and scientifically interesting rather than hazardous. The same math lets us compute B-plane targets, an imaginary plane perpendicular to the incoming velocity used to map where the traveller will pass relative to a planet. A dot on that plane represents the missed distance and the hemisphere of the pass. Moving that dot by tens of thousands of kilometers can change downstream sky positions by many Earth diameters, and that is why small updates in astrometry matter. Even the Earth-Moon system adds a fine line to the picture. Earth's gravity is strong but occupies a small, quickly moving region in heliocentric space. A distant pass shifts the visitor's apparent motion by tiny measurable amounts. An extremely close pass would break the object's smooth hyperbola into an Earth-centered swoop patched onto the wider solar curve. The Moon's contribution is smaller still, yet in precision fits it is included, because when we claim to understand the path, we mean we have accounted for every pull that could imprint a detectable signature on the track. One more gentle hand belongs to time itself. Orbital elements change slightly when we choose different reference epochs, and tiny numerical errors can grow if we extrapolate too far without fresh measurements. To keep gravity's portrait crisp, we regularly refit the orbit as new data arrives, anchoring the curve to real points rather than letting prediction drift. This practice mirrors a deeper truth about gravity-driven systems. They are predictable to high precision when forces are known and measurements are recent, and they remain understandable when uncertainties are carried honestly alongside the numbers. Taken together, these ideas show gravity as a composer more than a hammer. It writes melodies of motion that thread from deep space through our solar system and out again, layering a dominant solar theme with planetary harmonies and brief, delicate solos from tides and geometry. The music is continuous and deterministic, yet sensitive to timing and distance in ways that reward care. When we watch an interstellar visitor arc inward, accelerate, tilt slightly past a planet's reach and then ease back into the dark, we are watching a score performed exactly as physics wrote it, with no noise, no wasted notes, and no need for a conductor beyond the mass that everything shares. And as we measure each bar, positions on the sky, speeds along the line of sight, brightness changing with the angle of the sun, we translate that score into numbers that let us forecast the next measures accurately enough to keep our telescopes aimed and our understanding aligned with the gentle hand that guides everything that moves. Begin with a calm assumption: nothing hits the ground. The visitor does not collide with Earth, it simply passes near the sun, warms and sheds material. Even in that quiet scenario, the darkest plausible outcome is not fire, but shade. Dust released along the object's path can be drawn into elongated streams that Earth later plows through. Most grains are tiny, smaller than a human hair, so they never reach the surface. Instead, they enter high above us and burn into even finer particles, leaving a haze of microscopic material in the upper atmosphere. This haze can persist, especially if grains or their combustion products settle into the stratosphere, a layer where there is little rain to wash them out. The effect is subtle to the eye at first. Extra pink at sunrise, longer twilights, brighter noctilucent clouds at high latitudes. But measured instruments might notice a small reduction in the sun's energy reaching the ground. Shade, measured in watts per square meter, is the core of this thought experiment. A high-altitude haze dims sunlight most during the day and leaves infrared radiation from the surface to escape at night. That combination nudges surface temperatures downward. The cooling would not be dramatic like a volcanic winter unless the dust mass is enormous, but even small sustained reductions of a few tenths of a percent in sunlight matter for systems tuned to narrow margins. Photosynthesis runs on light, solar panels convert light to power, human mood and sleep respond to light cues every morning. Imagine the effect spread thin. Crops in marginal climates take longer to mature. Greenhouses adjust lighting schedules and burn more electricity. Solar farms produce slightly less at midday, exactly when grids expect them to peak. Individually, each change is small, but infrastructure stacks assumptions the way bricks build a wall. And missing bricks create stress elsewhere. The atmosphere reacts in layered ways. In the mesosphere and thermosphere, where meteoric ablation occurs, incoming dust feeds thin bands of metallic atoms like sodium and iron. These layers already exist, formed by ordinary micrometeoroids. A heavier dust stream would thicken them, altering how radio waves bounce and how airglow looks on sensitive cameras. In the stratosphere, ultrafine particles can serve as condensation nuclei, changing the formation of polar stratospheric clouds and influencing chemistry that touches ozone. The details depend on particle size, composition, and altitude. Silicates behave differently from carbon-rich grains. Sulfur-bearing compounds behave differently from pure ice. The most conservative expectation is extra scattering of sunlight and a slight shift in the balance between incoming and outgoing energy, a negative radiative forcing that tilts the climate engine toward cooler. The darkest edge of plausibility would be a multi-year, globally significant dimming if an unusually dusty fragmentation event coincided with Earth repeatedly crossing dense trails, a rare alignment but not forbidden by physics. Night skies would change in character. Meteor rates could climb during crossings of denser parts of the stream, bringing more frequent shooting stars. For the average person, this seems charming. For spacecraft operators, it adds drag variability and tiny sandblasting. The upper atmosphere puffs slightly when dust is abundant and solar activity is high, increasing the friction that slowly deorbits satellites. This is good for clearing dead hardware and bad for keeping useful satellites on station without extra fuel. Earth-observing missions that measure climate signals might need to recalibrate because haze above their lines of sight modifies both sunlight going down and thermal radiation coming up. Even small biases, if uncorrected, can propagate into large perceived trends when you integrate data across seasons. Human systems shift under light that is just a little weaker and a little bluer or redder, depending on particle sizes. Daytime lighting in offices and schools automatically compensates, but people who rely on natural light to set circadian rhythms could feel changes. Wake times drift, evening alertness lingers, sleep onset resists. These effects are gentle and vary widely between individuals, yet public health planners treat any widespread long-lived shift in daylight quality as a factor that touches mood disorders and productivity. City planners might notice a side effect on air quality indices, because high-altitude scattering can change how low-altitude pollution looks to remote sensors, forcing algorithm updates so we do not mistake stratospheric haze for urban smog. Agriculture is where the small, persistent shade matters most. Plants integrate light over days. A fractional reduction in photosynthetically active radiation can delay flowering, reduce yields at the edges of viable climates, and push farmers to adjust varieties and planting dates. Regions already near temperature or light limits, short-season grain belts, high-altitude terraces, high-latitude greenhouses, feel the squeeze first. Irrigation plans, fertilizer schedules, and pest pressures all respond indirectly because growth curves shift. Supply chains that run lean assume predictable harvest windows. A series of slightly delayed seasons in multiple regions can overlap in ways that stress storage and shipping. None of this implies catastrophe, but it does require coordination and communication so that small global signals are not misread as local failures. Energy systems face their own version of this. Solar farms would see capacity factors tick downward during affected months. Grid operators would compensate by dispatching more flexible generation, drawing on batteries, hydro or gas peakers. The cost is not just money, it is planning headroom. Margins set for heat waves and cold snaps now need to absorb an additional diffuse uncertainty about how bright next month will be at noon. Forecasting models that already include clouds and aerosols would ingest new data streams about high-altitude dust to keep day-ahead and hour-ahead predictions on target. Without those updates, forecasting errors might accumulate and lead to unnecessary curtailments or shortfalls, avoidable with calm adjustments but still real if ignored. A darker thought experiment extends to fragmentation nearer the Sun. Suppose the visitor breaks into many pieces at perihelion, producing a cloud of dust that the solar wind and radiation pressure spread along the orbit. If Earth's path intersects that debris more than once, we could experience repeated seasonal hazes, stronger during some years when orbital geometry focuses trails and weaker in others when geometry diffuses them. The pattern would resemble meteor shower cycles but expressed as transparency and colour changes rather than only streaks at night. In the stratosphere, particle lifetimes run from weeks to months, so the haze would not vanish overnight when the crossing ends. It would decay gradually, with weather patterns redistributing trace mounts and monsoons and storms removing what sinks lower. Public perception would be a separate challenge. Duller days, unusual sunsets, more meteors, and shifting power output create a narrative vacuum that rumour gladly fills. Experience with volcanic eruptions shows that even well-understood temporary stratospheric hazes can spark speculation. Clear repeated communication would be necessary. What we are seeing, what we expect next season, what is likely and what is not. The darkest outcome in social terms is confusion, not physics. Confusion can lead to poor choices, farmers planting the wrong varieties, utilities overbuilding or underpreparing, schools changing schedules in unhelpful ways. Information, timely, plain, consistent, keeps small physical signals from amplifying into unnecessary social stress. There are edge case physical risks that deserve honest mention, even if they sit far out on the probability curve. One is a dense clump of centimetre-scale fragments that survive into the lower atmosphere. Most would still burn up, but a heavy flux could produce localized sonic booms and shockwaves if a fragment explodes at high altitude, like a much smaller, less energetic version of historic airbursts. The chance that such a clump aligns with a populated area at the same time is tiny but not zero. Monitoring and early warning reduce surprise more than they reduce physics. People indoors and away from windows are protected from the main hazard of flying glass. Another edge case involves chemistry. If the dust contains unusual compounds that alter catalytic cycles in the stratosphere, we would watch for changes in ozone beyond the baseline variability driven by sunlight and dynamics. Instruments already stare at these layers. The plan would be to let them tell us if anything deviates from norms. Navigation and aerospace operations adapt as well. Airlines routinely adjust routes and altitudes to minimize turbulence and fuel burn. If high-altitude dust increases drag or changes temperature profiles on certain corridors, flight levels shift accordingly. Satellite operators budget extra station-keeping fuel when the upper atmosphere swells during geomagnetic activity. A dust-related tweak to drag forecasts would be folded into that planning. Deep space missions that rely on sunlight for power and for optical navigation would update their exposure and tracking strategies during hazy intervals. A small operational footnote that demonstrates how spacefaring depends on a transparent sky, even when the spacecraft are far above weather. The path from possibility to impact always runs through measurement. Sun photometers on rooftops and research stations measure aerosol optical depth, how much light is lost straight down. LIDAR systems profile particle layers by altitude. Spectrometers identify composition. Meteor radars count incoming grains and map their speeds, letting us trace streams back to their parent trails. Climate and crop models accept these inputs and forecast likely effects weeks to months ahead, with uncertainty bands wide at first and narrowing as data accumulates. The darkest plausible physical outcomes shrink in probability as measurements tighten. What remains is a manageable set of adjustments that institutions can schedule the way they schedule winter gritting, heat advisories, or flood preparations. This is not optimism, it is logistics informed by instruments. Under the umbrella of a thought experiment, it is important to separate fear from scale. The galaxy can deliver visitors that brighten night skies and feed headlines. The sun can warm and shred them into dust that paints sunsets. Earth can cross those trails and wear a thin veil for a while. The plausible dark side of that chain is a gentle, persistent shading that touches food, energy, and mood, at the margins more than it rewrites daily life. Planning for margins is what modern systems do best when given time. The work would be quiet, update forecasts, tune grid reserves, brief farmers, adjust satellite drag models, remind pilots and air traffic controllers what to expect, keep public messages simple and steady. Darkness, in this scenario, is a measurable dimness, not a permanent night. It yields to data, patience, and the same careful habits that let us read faint visitors in the first place. In that sense, even the darkest outcome lives within the reach of ordinary competence, spread across many hands, guided by the same calm attention we turn toward the sky. Dust changes sunlight in three main ways. It blocks some of it, it redirects some of it, and it very slightly warms the air that holds it. Scientists describe those three with simple terms: extinction, scattering, and absorption, and together they create the thin veil you can sometimes sense at sunrise and sunset. Extinction is the total dimming along the beam from the sun to your eye or a sensor. Scattering is the part of that dimming where light is not destroyed but sent off in new directions. Absorption is the part turned into a tiny amount of heat. The balance between scattering and absorption depends on the dust size, shape, and what it is made of. Bright, icy grains mostly scatter. Darker, carbon-rich grains absorb more. These properties translate into how colourful a sunset becomes, how long twilight lasts, and how much light reaches the ground for plants and solar panels. Tiny particles, much smaller than the wavelength of visible light, preferentially scatter blue light. This is the Rayleigh regime, and it is why clean air is blue. Larger particles, roughly the size of visible wavelengths and upward, from a few tenths of a micrometer to several micrometers, behave in the Mie regime and scatter more evenly across colours, often pushing light forward rather than backward. A high-altitude haze dominated by these slightly larger grains tends to wash the sky toward white near the sun, extend twilight by feeding light from just below the horizon, and redden the solar disk because the bluer parts of the beam are scattered out of your direct line of sight more efficiently. The exact tint you see depends on the size distribution. Shift toward finer particles, get more colour separation. Shift toward coarser, get more uniform whitening. Two simple measurements summarise the strength of this veil: aerosol optical depth AOD and the angstrom exponent. AOD tells you how much of the sun's light is removed by particles along a vertical path. Higher AOD means thicker haze. The angstrom exponent is a slope that hints at average particle size. Larger values imply finer particles. Smaller values imply coarser ones. Ground stations with sun photometers read these numbers throughout the day. A stable stratospheric haze from meteoric dust would show up as a modest AOD bump and a characteristic slope, indicating submicron sizes. Satellites cross-check from above, while LiDARs profile how the particles sit by altitude. With these three tools, AOD, size slope, and height profiles, we can say not just the sky is hazy, but the haze is this thick, this fine, and at this height. Height matters because the atmosphere is layered. In the troposphere, the lowest layer where weather happens, dust mixes, clumps, and rains out relatively quickly. In the stratosphere, the calm layer above, there is little rain and fewer vertical motions, so particles can persist for weeks to months. Interstellar dust that ablates into nanometer to submicrometer, meteoric smoke at 70 to 110 kilometers can slowly settle downward and feed the lower thermosphere and upper mesosphere with material that eventually trickles into the stratosphere. Once in the stratosphere, these ultrafine particles scatter sunlight efficiently relative to their mass. They also serve as surfaces for chemical reactions and as seeds for special clouds under very cold conditions. The Brewer-Dobson circulation gradually transports stratospheric aerosols from the tropics toward the poles and downward, shaping where the veil is thickest season by season. Colour changes in the sky follow simple geometry. When the sun is high, the light path through the air is short, so a thin haze barely shows. You get mild whitening and a softer contrast between blue sky and clouds. As the sun drops, the light path length grows dramatically, so each kilometre of air adds its small effect to a large total. The direct sun reddens because shorter wavelengths are preferentially scattered out, while the sky around it brightens with a pale aureole created by forward scattered light. After the sun sets, the twilight zone glows because high-altitude layers still catch sunlight and send it down to you along slanted paths. If those layers include a fine veil, the twilight can last longer and look smoother, with a more gradual fade from yellow to greenish to blue-grey. These are visual cues that the sky's thin veil is at work. Polarization is another fingerprint. Clear, clean skies polarize strongly at right angles from the sun, because Rayleigh scattering dominates. Add a veil of me scattering aerosols, and the degree of polarization drops and the angle of maximum polarization shifts slightly. Polarization-sensitive cameras and even well-calibrated sunglasses can reveal these patterns, but you don't need special gear to notice practical effects. Photographers see flatter contrast at midday, astronomers see brighter sky backgrounds that reduce the limiting magnitude, and remote sensing instruments must correct for the veil to avoid biasing measurements of land colour, ocean colour, and vegetation indices. The veil changes not just brightness, but the spectrum, the distribution of colours across wavelengths. Plants care about photons in the 400 to 700 nanometer band known as PAR, photosynthetically active radiation. A thin aerosol layer usually reduces total PAR slightly, but can increase the fraction of diffuse light. Diffuse light penetrates canopies more evenly, sometimes improving photosynthesis in dense crops, even as total sunlight dips. The net effect depends on crop type and leaf arrangement and background climate. Greenhouses can compensate with supplemental lighting time to maintain photoperiod cues. Outdoor agriculture would adapt by the shifting sowing dates, swapping varieties with different light requirements, or using anti-reflective films and canopy management to make better use of diffuse light. The veil's spectral tilt also nudges UV at the surface. Fine aerosols can reduce UVB modestly, interacting with ozone levels to change the UV index by small but measurable amounts, relevant for both skin protection and vitamin D synthesis. Solar energy systems feel the veil in a detailed way because solar cells respond differently to different colours. Silicon photovoltaics are most efficient in the red and near-infrared portion of the spectrum. Thin film technologies can have distinct spectral responses. A veil that trims blue more than red reduces short-circuit current slightly, but may leave overall efficiency near expectations whereas a strongly absorbing carbonaceous veil that warms the air and removes light across the board lowers output more evenly. Tracking systems that follow the sun benefit from forward scattered light that still comes from near the solar direction, while fixed tilt arrays benefit somewhat from the extra diffuse component that reaches their planes from the whole sky. Forecast models incorporate aerosol optical depth and spectral shape to predict day-ahead power. Without those inputs, operators would see a consistent bias during hazy periods. In the upper atmosphere, interstellar dust products add to the long-lived meteoric metal layers, sodium, iron, magnesium, created when grains vaporize and atoms recombine. These layers affect laser guide star adaptive optics by providing targets that glow when excited by lasers, and that they influence the brightness and altitude of noctilucent clouds, polar mesospheric clouds, that form in the cold summer mesosphere around 80 to 85 kilometers. Noctilucent clouds need water vapor, very low temperatures, and tiny seed particles. Meteoric smoke provides those seeds. If the supply increases, these clouds can become slightly more frequent or brighter in the seasons and latitudes where they already appear. Seen from the ground, this looks like silvery filamentous clouds that glow after sunset. Another subtle sign that dust has met sunlight in the sky's upper rooms. Chemistry rides on surfaces. Ultrafine particles offer sites where trace gases can stick and react. In the stratosphere, this mostly belongs to sulfate aerosols after volcanic eruptions, but meteoric smoke can play a quieter role by hosting reactions that shuffle nitrogen and hydrogen oxides, indirectly influencing ozone in ways that are small compared to temperature-driven dynamics, but not zero. These same particles absorb and emit infrared weakly, adding minuscule heating or cooling rates that, integrated over months, can slightly shift the vertical temperature structure. Heating influences stability. Stability influences how layers mix. Mixing influences how long the veil stays aloft and how evenly it spreads. Gravity waves, ripples in air created by mountains, storms, and jet stream meanders, can loft and concentrate aerosols into thin, fan, wavy sheets that instruments detect as ripples in backscatter. Seen at twilight, they paint the sky with faint parallel bands. These patterns are not dangerous. They are signposts that energy and momentum are moving upward from the weather below into the calmer layers above, and the veil is thin enough to trace those motions like dye in water. Over time, particles change size through coagulation, sticking together, and by picking up or losing material. Ultrafine meteoric smoke tends to clump into slightly larger aggregates, which scatter light differently and settle a bit faster. Settlement rates are slow in the stratosphere, millimeters per second, but gravity never stops, so layers descend over weeks to months. As they fall into the troposphere, weather takes over and removes them with rain. This life cycle, creation high up by ablation, slow descent, removal by weather, means the veil is self-limiting, unless it is replenished regularly by repeated dust injections. If an interstellar visitor sees multiple streams, you could see seasonal pulses superimposed on that slow decay. Thicker veils after Earth crosses a fresh trail, thinner veils after clean periods with little replenishment. Visibility at ground level changes in intuitive ways. Even if the veil sits high, forward scattered light washes distant contrasts, making mountain ranges look a step closer to the background sky tone. Astronomical extinction coefficients increase. Photographers notice that polarized filters help less than usual because the scattering phase function has shifted. Air quality indices, which mostly respond to near-surface particles, may not capture the full story because the veil lives above most pollution sensors. That is why dedicated sun photometers and satellite retrievals, which look column-wide, are needed to tell the whole tale. Communication between agencies prevents confusion. A hazy sun is not always local smog. Sometimes it is a global high-altitude film. For instruments and observations, corrections are straightforward once the veil is measured. Radiometers apply AOD to calibrate top-of-atmosphere reflectances, Astronomers apply nightly extinction coefficients to standardize magnitudes. Climate models ingest aerosol fields to compute radiative forcing layer by layer. The single scattering albedo, the fraction of scattering versus total extinction, and the asymmetry parameter, how forward the scattering is, control the details. LiDAR depolarization ratios reveal particle shape, low depolarization for spherical droplets, higher for irregular dust. Meteor radars count influx and speed, feeding back to estimates of how much mass the atmosphere added today. These numbers turn a visual impression into a quantitative description that can be compared across sites and seasons. The human eye remains a sensitive detector even without instruments. Soft-edged shadows at noon, a milkier blue around the sun, sun pillars and halos more often when ice crystals share the sky with aerosols, a more pronounced belt of Venus, the pink anti-solar band, after sunset. Each is a small experiment run by the atmosphere and reported directly to your senses. None of this implies harm on its own. It is evidence that dust and sunlight are playing their familiar game of scatter and shade in a slightly different ratio than yesterday. All of these processes scale with the amount and character of dust. A light veil yields delicate optical effects and small reductions in surface light. A thicker veil sustained nudges temperatures and plant growth measurably, shifts solar output forecasts by a few %, and asks observers and operators to apply careful corrections. Composition shapes the edge cases. Darker particles add more absorption and local heating aloft. Brighter particles mostly scatter and cool the surface slightly. Size sets the colour and forwardness of the scatter. Height sets the lifetime. Mix them and you get the sky you see. The thin veil is not a mystery once the pieces are laid out. Dust enters high, is processed by sunlight and collisions, settles slowly, and is eventually washed out. Along the way it changes the path and palette of light in ways that can be measured and predicted. When an interstellar visitor adds to that veil, it simply borrows these existing pathways. Ablation to smoke, smoke to layers, layers to twilight, twilight to ground effects. Understanding the chain lets us separate spectacle from signal, enjoy the sunsets, correct the instruments, adjust the forecasts, and keep track of how much light, in what colours, reaches the living and working surfaces of the world. Routines are agreements we make with the world about what tomorrow will look like, and they work because key inputs, light, temperature, timing, stay within a familiar range. When the sky's brightness shifts even slightly for weeks or months, those agreements loosen. Power grids, for example, are scheduled on the assumption that midday sunlight is reliably strong. Operators plan which generators will be online hours to days ahead, counting on solar farms to deliver a predictable slice of daytime power. A small, persistent dip forces the grid to lean more often on flexible resources, batteries, hydro releases, quick start gas turbines, and to carry a bit more reserve. That reserve costs money and attention, which were previously earmarked for heat waves, cold snaps, or maintenance windows. Forecasting fixes most of the strain, but forecasts depend on measuring the haze correctly and feeding it into models. When those inputs are late or off by a little, operators pad margins, and padding becomes the new routine. Agriculture is tuned to a calendar of accumulated light and temperature. Many crops measure day length to decide when to flower. Others care more about the total amount of usable light over time. A consistent reduction in photosynthetically active radiation can delay maturity by days to weeks at the edges of viability. Farmers adjust by choosing varieties with slightly shorter growing seasons, shifting sowing dates, or changing plant density to make better use of diffuse light. These are practical choices, but they ripple. Seed orders change, labour schedules slide, irrigation plans move, and harvest windows crowd each other if multiple regions shift in similar ways. Storage and transport then carry the knock-on effects. Elevators fill at off-peak times, trucking and rail slots overlap, and export schedules shuffle. None of this is dramatic, yet every link nudges the next. so institutions used to just-in-time flows need a little more slack in the chain. Buildings and cities run internal clocks that listen to the sky more than we notice. Office lighting systems often dim and brighten automatically based on daylight sensors, aiming to keep a consistent interior brightness while saving energy. If midday is regularly dimmer outside, those systems draw more power inside. Schools that rely on natural light to keep students alert in morning's hours may find classes a touch sleepier, not because anyone slept less, but because the dawn cue that primes alertness softened. Transit schedules for commuters, especially those who walk or bike, feel different under longer twilights. Some people leave earlier or later to match what feels right, quietly altering peaks on buses and trains. Public health planners watch these behaviour shifts because light stabilises circadian rhythms, and even small widespread changes in morning light can move average sleep onset and wake times, with downstream effects on mood and concentration that are modest individually and meaningful at population scale. Weather-sensitive businesses fold the new variable into their routines. Construction crews plan pours and finishes around expected drying rates and temperatures. A dimmer midday and slightly cooler surface can stretch cure times, pushing subsequent steps a day. Retail energy pricing tied to solar production sees flatter midday dips, altering when it is cheapest to run large loads in homes and businesses. Data centers that use free cooling from outside air for extend those windows in cooler conditions, saving energy but also changing when backup generators must be tested to avoid overlap with low solar hours. These micro adjustments add up to a different daily cadence behind the scenes, one that still looks smooth to the public if the changes are anticipated and communicated. Aviation and space operations recalibrate quietly. Airlines optimize routes and altitudes based on winds, temperature profiles, and fuel burn. If high-altitude haze shifts thermal structure, the preferred flight levels on some corridors drift. Satellite operators adjust station-keeping fuel budgets when upper atmosphere drag varies, and they update optical navigation exposures if sky brightness changes around the sun. Ground-based astronomy and Earth observation revise their calibration routines to account for extra extinction and scattering, inserting more standard star checks or alternative viewing geometries. These are routine maintenance acts, but they depend on having clear shared numbers about how the atmosphere is behaving above the weather layer. Education and work patterns show how much we anchor to light cues without realizing it. Morning classes that depend on bright rooms to boost alertness may need subtle schedule shifts, earlier recess to catch higher angles of light, later labs to match student focus. Remote workers who set their own hours tend to follow sunlight. A prolonged period of softer midday brightness can push more activity into late morning and early afternoon, changing network loads and the timing of meetings across time zones. Hospitality businesses that rely on golden hour foot traffic see slightly longer twilights and adjust staffing to meet the new pace of arrivals. These are gentle drifts, but they often happen all at once across a region, so signals like traffic peaks and restaurant reservations move together, which can surprise planners if they only track clocks and not light. Healthcare routines meet light at multiple points. Hospitals schedule certain therapies that leverage circadian biology, for example, timing bright light exposure in mood and sleep treatments. If the ambient baseline dimmed, clinical protocols might increase the intensity or duration of artificial light to maintain effectiveness. Elder care facilities, where residents' circadian systems are more fragile, pay close attention to morning light to anchor stable daily rhythms. They adjust window time, outdoor walks, or light boxes to substitute for softer skies. Even at home, people who use morning sunlight to anchor wakefulness may find a weaker cue needs a conscious replacement. A few minutes near a bright window, a lamp on a timer, to keep sleep consistent. Finance and insurance turn slow environmental changes into risk scores and premiums. A few % drop in solar generation across a portfolio for a season moves revenue projections, hedges and contracts that assume typical irradiance get repriced or rewritten to include an aerosol clause. Crop insurance models that estimate yield distributions absorb haze as a variable alongside rain and heat, changing payouts for marginal seasons. Municipalities that sell long-term bonds tied to utility revenues or agricultural taxes update their forward guidance to reflect slightly larger uncertainty bands. Investors do not fear small changes. When they are quantified, they fear surprises. So a new routine emerges. Regular aerosol updates join familiar weather bulletins, and dashboards show not only temperature and precipitation, but also high-altitude clarity. Culture and daily joy bend with the light too. Photographers chase sunsets that become more frequent and gentle. Tourism boards highlight longer twilights and clearer noctilucent displays where they occur. Outdoor events shift start times to catch the best glow. City lighting plans, aiming to reduce light pollution, revisit dimming schedules because the night looks brighter near the horizon, under forward scattering veils. Adjustments keep the stars visible while paths stay safe. Planetariums and science centres lean into public curiosity with simple exhibits explaining why the sky looks different, turning potential unease into understanding and even appreciation. Communication is a routine like any other. Practiced often, it becomes the background hum that keeps communities aligned with the environment they share. Logistics and manufacturing built on tight timing find room for a bit more slack. Cold chain operations schedule fewer daylight-dependent loading windows to avoid temperature excursions when sunlight is unpredictable. Warehouses shift some picking and packing to earlier or later blocks that match worker alertness curves. Just-in-time lines add a small buffer of critical parts to cover minor port or rail delays caused by rescheduled harvests up the chain. The cost of these cushions is modest compared to the resilience they buy, and once installed, they remain as a guardrail against other surprises unrelated to the sky. Policy and governance express routine through rules and incentives. Utility regulators may allow temporary adjustments and capacity payments for flexible generators while models catch up. Agricultural extensions distribute simple bulletins, variety recommendations, sowing windows, irrigation tweaks, based on updated light forecasts. Education departments provide guidance to schools on maintaining healthy light levels in classrooms during dimmer seasons. Public broadcasters include a short sky clarity index in daily weather segments so citizens learn the pattern and plan without anxiety. In each case, the action is small and the signal calm, yet the message is consistent. We watch, we measure, and we adapt with ordinary tools. At the household level, routines fold in new habits almost invisibly. People set smart lights to brighten a little earlier, park solar chargers closer to windows for longer, start evening walks a bit sooner to catch remaining light, or brew the first coffee under a brighter lamp that anchors wakefulness. Gardeners pick cultivars that tolerate lower light or adjust pruning to open canopies for diffuse illumination. Home solar owners glance at a new chart in their app that explains why output dipped and when it will likely recover, and they schedule high-load appliances for the sunniest expected hours based on improved forecasts. These micro-adjustments feel natural because they are simply extensions of what people already do with weather. The most fragile routines are the ones that assume straight lines forever. Growth that never pauses, schedules that never flex, models that never update. Light teaches a softer lesson. A small sustained change is an invitation to recheck assumptions and add grace to systems. Where there is slack, minor shocks are absorbed. Where there is none, even a small nudge rattles. This is not a moral argument, but a practical one. Resilience is cheaper than repair. Adding a bit of buffer to grid reserves, harvesting windows, classroom lighting, air traffic planning and public messaging costs less than the friction of constant surprises. As routines incorporate these buffers, they become less fragile by design. The thread tying all of this together is feedback. We measure the sky clearly, publish the numbers simply, and let each sector translate them into its own small adjustments. In doing so, we change the definition of normal, not by pretending nothing moved, but by moving with it a little, deliberately. The sum of those small moves is a society that keeps working smoothly under a sky that is a touch different for a while. The rhythm remains recognizable, alarms still ring, ovens still preheat, buses still arrive, emails still pile up, children still ask for 5 more minutes before bed. The difference is that behind those ordinary moments, many hands have shifted dials by a notch. Power schedulers, teachers, farmers, pilots, coders, nurses, parents, so that fragility becomes flexibility, and the day takes its familiar shape under a light that has subtly changed. Signals are small pieces of reality that ask to be understood. Stories are the frames we put around those pieces, so they make sense to us. When something unfamiliar appears in the sky, the signals come first. A faint moving dot, a curve on a chart, a spectrum with a gentle slope, a forecast that shifts by a few percent. None of these feels like a story on its own. They are numbers and images that require careful treatment, calibration, context, comparison, to mean anything stable. But human minds do not wait. We reach for patterns, motives, and endings because narratives help us decide what to do next. This is natural and often useful. It is also where imagination can run ahead of evidence, turning whispers into declarations and possibility into certainty before certainty is actually available. One step toward balance is to keep the difference clear between what we saw, what best explains it so far, and what we are still testing. Scientists sometimes call these tiers data, model, and hypothesis. Data are the positions, brightnesses, and timestamps. Models are the orbits and physical interpretations that fit those points. Hypotheses are the if-then ideas we put on the table to see which survives new measurements. Confusion begins when these layers collapse into each other, when a preliminary model is treated as data, or when a hypothesis is announced as if it had passed all tests already. A simple habit helps: match words to strength. We measured is different from we infer, which is different from we suspect, which is different from we imagine. Each word sets expectations for how easily the claim should change if tomorrow brings better measurements. Uncertainty is not a flaw to be hidden. It is a measurement in its own right. Error bars and confidence intervals feel like footnotes, but they are maps of where knowledge is solid and where it bends. In signals from the sky, uncertainty often starts large and shrinks as observations accumulate. This shrinking is a story worth telling because it shows progress honestly. The track is wide on day 1, narrower on day 3, and a well-marked curve by day 7. When people see uncertainty behave this way, named, quantified, and reduced by new evidence, they are more willing to live alongside it without anxiety. They learn to expect estimates that move a little and to value updates that explain why they moved. Imagination fills gaps with archetypes because archetypes are comfortable tools. Visitors from outside our system invite 3 classic tales. The omen, something bad approaches; the gift, something wonderful arrives; and the test, we are being measured. All 3 are ancient patterns applied to a modern signal. The omen story is fueled by negativity bias, our tendency to pay more attention to possible harm. The gift story grows from optimism and wonder, our desire to find meaning and opportunity. The test story springs from agency detection, the habit of assuming intention behind events. None of these stories is automatically wrong, they are simply not evidence. Recognizing them at work in our own thinking does not drain life of meaning. It helps us choose meanings that do not fight the facts. Media ecosystems amplify whichever stories fit their incentives. Fast channels reward novelty, clarity, and emotion. Slow channels reward depth, nuance, and revision. A wise public diet uses both. Fast updates can tell you that a new object was found and roughly where it is. Slower formats, explainers, interviews with researchers, data visualizations, can show how the orbit is fitted, why brightness changed, and what the remaining uncertainties are. If you notice that a source never shows its inputs, never reveals uncertainty, and never revises earlier claims, you're not looking at signals, you're looking at performance. Good storytelling does not remove mystery. It frames it so you can live with it and learn from it. Rumours follow paths that data rarely do. They grow when signals are sparse, language is vague, and time feels tight. One antidote is to make the smallest reliable unit of truth widely available. In skywatching, that unit might be a current ephemeris with an uncertainty band, a light curve with a clear timestamp, or a simple set of "not this" statements. Not this is powerful. Not a satellite at these times and places, not a known asteroid on this orbit, not a spacecraft according to public tracking. Negation cleansed the field so imagination does not waste energy on dead branches. It also builds trust, because stating limits openly is a mark of seriousness. A helpful mantra for communities is slow down, zoom out, check sources, ask scale. Slow down, an extra hour of patience often converts confusion into clarity as new measurements arrive. Zoom out, ask how this signal fits longer patterns, previous visitors, known meteor streams, seasonal transparency changes, so you can tell novelty from familiarity. Check sources. Rely on outlets that cite data you can inspect or reputable intermediaries who are transparent about where they got their information. Ask scale. Is the effect measured in percent or in orders of magnitude, in days or in years, in local skies or global ones? Scale protects you from mistaking a small interesting shift for a sweeping change that demands dramatic reaction. Art, literature, and ritual give imagination a safe place to play while analysis does its slower work. Paintings and poems do not need error bars to be true in their way. They help people feel the size of the cosmos and their place within it. Planetariums and community nights under the stars make uncertainty friendly by letting people ask questions face to face, see instruments up close, and hear phrases like, "We don't know yet," spoken without fear. The more often a community experiences honest not knowing, paired with steady progress, the harder it is for panic or cynicism to take root when the next unfamiliar signal arrives. Language choices shape public mood. Metaphors of invasion and threat push attention to the edges of plausibility. Metaphors of weather and seasons encourage planning and patience. Saying a thin, high veil that slightly dims the sun leads to different actions than a shroud over the earth, even if both are describing the same measured AOD increase. Science communication benefits from metaphors that carry scale and mechanism quietly inside them. Veils, lenses, tides, echoes, so that as understanding deepens, the metaphor still fits instead of breaking and forcing a headline rewrite. Cognitive biases are part of every mind, including expert minds. Confirmation bias pulls us toward interpretations that match what we already believe. Availability bias makes recent vivid events, like a spectacular meteor or a famous comet, feel more likely than statistics justify. The sunk cost fallacy keeps bad explanations alive because we invested time or reputation in them. The way through is procedural humility. Pre-register what would change your mind. Welcome adversarial collaboration, where independent teams try to break each other's favourite models, and separate the role of advocate from the role of analyst. In public, this looks like scientists saying out loud, if we detect this feature, our interpretation stands. If we do not, we will adopt the alternative. Watching that process lowers the temperature and raises confidence that the story is attached to the signal, not to anyone's pride. Visuals can either clarify or confuse. A clean plot with labelled axes, a scale bar, and a note about uncertainty turns a rumour into a conversation. A dramatic rendering without Barnett scale can do the opposite, inflating a small, distant object into a looming presence. Good visuals show what is measured and what is imagined, real trajectories in solid lines, extrapolations in dashed, observed brightness in dots, model fits in gentle curves, true colours marked, false colour images labelled. This is not pedantry. It is the difference between learning and being carried along by mood. Communities benefit from a few shared, steady signals that everyone can check. A public ephemeris web page, a daily sky clarity index, a meteor count from volunteer radio stations, a short bulletin that says what changed, what didn't, what's next. These anchor points give people a place to stand. When friends share overexcited posts, you can reply with a link to a calm, current chart rather than an argument. Over time, the habit becomes cultural. Before we leap, we look. Before we worry, we measure. Before we conclude, we compare. Imagination is not the enemy of truth, it is the scout that finds paths truth may later walk. The task is to keep the scout from building cities where there is only a trail. We can do that by letting signals lead, by treating uncertainty as information, by matching words to strength, by choosing metaphors that scale, and by building public rituals of revision, regular updates that treat changes as growth, not as failure. In this way, a faint dot crossing the sky becomes two gifts at once: new facts about the world and new practice at living with the space between first notice and firm understanding. The first gift teaches us how the universe works. The second teaches us how to be patient, curious neighbours under the same slowly changing light. Preparation without panic begins with a posture, not a purchase. Notice early, speak plainly, act proportionally, and revise quickly. The first layer is measurement you can trust. That means a small set of instruments and data products that are always on, always calibrated and publicly visible. Wide-field sky surveys for the object's path and behaviour, sun photometers and lidars for aerosol optical depth and height, meteor radars for dust influx, radiometers for surface solar irradiance broken into direct and diffuse parts, and a few spectral sensors to watch colour shifts. Each stream has a simple shared format with timestamps, uncertainty, and location. Each feeds a daily summary. How much light changed, at what wavelengths, and at what altitudes. The point is not to flood people with raw numbers, but to sustain a stable heartbeat of information that does not depend on a headline to exist. The second layer is translation, turning measurements into guidance for sectors that depend on light. Energy operators need day-ahead and week-ahead irradiance forecasts that include aerosol scenarios and confidence intervals. Agriculture needs regional PAR anomalies, expected shifts in growing degree days, and crop-specific advisories. Spring wheat, expect +5 to 7 days to maturity. Consider variety B in latitude above X. Aviation needs updated vertical temperature and density profiles for fuel planning and turbulence avoidance. Satellite teams want drag forecasts at 200 to 500 kilometers and sky brightness around the sun for optical navigation. Public health departments want light-at-wake indices to advise on circadian-friendly routines. Each translation is a concise one-page product with thresholds coloured like traffic lights, backed by links to the underlying data so trust can be checked rather than assumed. Playbooks keep action calm. A good playbook has the triggers, actions, and owners. For grids, if regional midday irradiance forecast deviates by greater than 3% for at least 5 consecutive days, then increase spinning reserve by X%. Activate battery smoothing schedules and publish a public note explaining the reason and timeline. For farms, if PAR anomaly exceeds -5% during critical flowering windows, then advance irrigation by 1 day and consider foliar feeding. Deploy row covers for specialty crops where feasible, for schools and hospitals. If morning light index drops below threshold for 2 consecutive weeks, then increase indoor light intensity during first 90 minutes of day by Y lux. Encourage brief outdoor exposure when safe and monitor sleep timing surveys. For space operations, if exospheric density rises above baseline by Z%, increase station keeping cadence and replan deorbit windows. Tying each trigger to a clearly owned action prevents handoffs from fraying and keeps effort proportionate to the signal. Communication is infrastructure. It should be frequent, short and boring in the best sense, so that updates feel like weather, not drama. A daily sky clarity line item in weather reports, a weekly sector brief, and a standing Q&A channel hosted by a trusted local institution, public radio, extension services, science centres create predictable touchpoints. Words matter. Veil, haze, anomaly, and percent change carry scale better than metaphors that either minimize or alarm. Each message shows what changed, what did not, what will be checked next, and when the next update arrives. Corrections are framed as growth. We reduced the uncertainty because 3 new stations reported. Forecasts for next week shifted from -2% to -1%. Resilience is a sum of small buffers added before you need them. Energy systems can pre-contract a modest amount of flexible capacity and demand response, upgrade forecasting pipelines to ingest aerosol fields, and tune inverter settings on solar plants to handle higher diffuse fractions without tripping. Agriculture can stock seed varieties with slightly different maturities, expand extension hotlines during sensitive seasons, and align crop insurance models with aerosol-aware yield distributions, so relief flows match reality. Cities can audit daylighting in schools and clinics, placing inexpensive light meters and calibrating automated systems so indoor brightness remains healthy under dimmer skies. Transit and workplaces can permit small schedule flex to accommodate shifted circadian cues, reducing the friction that strict start times create when dawn is less energizing for a while. Preparedness includes drills, not sirens, checklists. A twice-yearly dim day exercise asks, if midday irradiance were -5% for 2 weeks, what would each team do? Grids run a simulated dispatch. School districts test classroom lighting presets. Hospitals rehearse bright light therapy timing. Agriculture offices run phone trees to co-ops. Satellite operators simulate increased drag. After-action notes capture friction points, missing data, unclear thresholds, duplicate responsibilities. The next drill is cleaner. Drills strip novelty from response so the real event is just work, not shock. Equity is a design constraint, not an afterthought. Dimmer days pinch those with fewer resources first. Small farms, schools with poor lighting, households without flexible schedules, clinics already stretched. Preparation budgets are sliced for targeted support. Grants for circadian-friendly lighting in public schools and elder care. Subsidized advisory services for smallholders. Backup credit lines for co-ops facing slightly delayed harvests. Community cooling and light rooms for mental health during long overcast plus haze periods. Communication channels include languages and formats used by the communities most affected. Measurement networks place instruments where people live and work, not just on research campuses, so local conditions are visible and actionable. Misinformation thrives in gaps. Shrink the gaps. A standing myth versus measurement page lists common claims and the current best evidence. Is this a sign of X? No. Here's the measurement that rules it out. Is the dimming global? Here are regional maps. Will it last years? Here's the scenario band with best, median, and worst cases. Updates are time-stamped, archived, and easy to share. Trusted messengers, teachers, nurses, farmers, pilots receive short briefings they can relay in their own words. Public participation strengthens the loop. Citizen science apps let people point phones at the sun with safe sensors or via sky luminance, estimations, photograph twilights with calibration, and report sleep timing or plant phenology. The data is flagged as community-sourced and used to refine local models, a visible sign that attention is valuable. Standards prevent chaos. Data units, file formats, and APIs are agreed upon across agencies and countries, so models and dashboards plug together. Uncertainty is mandatory in every figure. Plots include scale bars and ranges, not just single lines. Maps use consistent color ramps for aerosol optical depth and irradiance anomalies, so a glance means the same thing in different regions. Forecast dashboards show ensemble spreads, not just medians, teaching users to expect variability and to plan with ranges. Governance has to be clear enough to move and humble enough to adapt. A small cross-sector tasking group meets on a schedule with the authority to synchronize playbooks, request resources, and issue advisory levels that are descriptive, not punitive. Minutes are public, decisions cite data, sunset clauses ensure that temporary measures expire or are renewed intentionally. An independent review board checks models for bias and blind spots, publishing constructive critiques so the shared toolkit improves. Preparedness also means saying what you will not do. You will not overreact to single outlying measurements. You will not suppress uncertainty to look confident. You will not treat a modest, managed dimming as a crisis to be solved by rash interventions. You will not let a rare edge case risk overshadow the everyday work of tuning forecasts, supporting workers, and minding vulnerable neighbours. Stating these boundaries prevents escalation and keeps attention on practical steps that pay off regardless of how the sky evolves. Engineering detail matters. Solar plants can adjust maximum power point tracking to spectral shifts, add bifacial modules or skyward reflectors where terrain and ecology permit to leverage diffuse light. Keep panels cleaner because small losses loom larger when input is lower. Greenhouses can shift supplemental lighting from fixed timers to PAR-triggered controls, preserving plant signals while minimizing cost. Data centers compare aerosol-aware irradiance with cooling strategies to avoid coincident peaks. Precision agriculture can use canopy-level sensors to maintain optimal light interception under changing diffuse fractions, trimming nitrogen or irrigation where growth slows to prevent over-application. Airlines can fuse aerosol forecasts with contrail avoidance and fuel burn models to find routes that meet both climate and cost aims when upper air conditions change. Public rituals help people metabolize change. Community twilight walks with short talks from local scientists, school projects that track plant growth under different light, art installations that translate aerosol data into gentle soundscapes. These are not extras. They are the social glue that keeps we're watching and adjusting believable and cooperative. When the sky looks different, giving people a way to look together turns private unease into shared curiosity. The feedback loop closes with metrics. Define what success looks like. Forecast errors trending down, grid reserve use stable, crop yields within adjusted bands, school attendance steady, sleep timing variance unchanged or improving, misinformation claims decreasing, vulnerable population support uptake adequate. Report these alongside the physical indices. If a metric drifts, do not mask it, trace the cause and adjust the playbook. Preparation is a living document. Panic is a frozen snapshot. Living documents iterate. Finally, remember proportionality. Most plausible scenarios ask for steady competence, not heroics. Competence is built from habits. Measure carefully, publish clearly, plan small, act early, test often, help the nearest person first, and let tools improve as you learn. In that rhythm, a dimmer season becomes a taught lesson rather than a wound. The lesson is simple and durable. A community that can change a little on purpose can keep most things the same that matter. Under a slightly altered light, meals are still cooked, lessons still taught, crops still grown, power still delivered, night still restful because the work of preparation was done openly, modestly, and in time. Most paths lead to calm. The most likely outcome for a passing interstellar visitor is a safe, unremarkable flyby that rewards attention more than alarm. It arrives faint. It brightens modestly as sunlight and geometry improve. And then it fades into the outer dark while we file away better measurements and a few new comparisons. In this ordinary case, nothing crashes, nothing lingers except lessons, and this main signal felt on the ground is curiosity itself. Telescopes track, models tighten, spectra whisper about surface chemistry, and the public sees a handful of news items and some pretty sky photos. In a world where rare surprises get the loudest microphones, it is worth saying plainly, most skies stay ordinary most of the time, and the value hides in the patient sharpening of our picture rather than in spectacle. A step beyond the most likely is the moderately likely. A low-activity object that releases a little dust, grows a faint coma, and perhaps spawns a thread-like tail that observers with dark skies and good optics can record. If Earth later crosses a diffuse portion of that trail, a meteor shower could tick up a notch for a night or two, offering more frequent, fine streaks that delight night watchers without changing anything essential down here. Instruments notice, of course, they always do, Meteoroid radars count more pings, sky brightness around the sun flattens slightly from forward scattered light, and solar farms measure a percent level dip compared to a clear day with no veil. But these changes are small enough to fall inside the envelope of ordinary variability, handled as a matter of routine forecasting and calibration. Less likely, but still within the realm of plain plausibility, is a more active passage. The visitor fragments gently or vent strongly near its closest approach to the sun, filling a narrow slice of space with finer dust. In this scenario, sunsets lean warmer for a season, twilights last a breath longer, and noctilucent clouds at high latitudes appear a little more often, or glow a little brighter where they already live. Crop advisors issue short notes that certain regions might see slightly slower growth rates. Grid operators carry a bit more flexible capacity during the affected weeks. Astronomers adjust extinction coefficients in their nightly calibrations and keep going. The world does not bend much. It notices, updates, and continues. Unlikely outcomes exist, and naming them without inflating them is part of honest storytelling. A dense, repeated crossing of fresh, dust-rich trails could produce a multi-season stratospheric veil, strong enough to shave a small but measurable fraction from surface sunlight across large regions. That nudge would touch energy planning and agriculture more noticeably, inviting the kind of proportional responses described earlier: forecast-aware scheduling, variety shifts, supplemental light in sensitive settings, careful public communication. Even here, the stress is margin-sized, not world-sized, and steadily decreases as dust settles and the sky clears. Farther out on the tail of possibility sit scenarios where fragments reach lower altitudes. The physics allows loud booms and bright airbursts on rare, unlucky alignments. Those are edge cases that become less mysterious, and therefore less frightening when they are explained with scale, probability, and the simple indoor advice that covers the main hazard, glass, from similar better-known events. The beautiful lives in every branch of this tree. In the quiet branch, beauty is the elegance of orbits drawn from sparse points, the way error bars shrink as if stitched by invisible hands, and the shared cadence that lets dozens of observatories behave like one instrument. It is the calm thrill of a clean spectrum where a slope tells a story about ice and dust forged under a different sun. It is the choreography of global cooperation, observers chasing the same moving target from dusk to dawn across longitudes, coders refining pipelines so false alarms fall away, students adding their first measurements to a public archive that remembers their work. In the modest activity branch, beauty shows up as sky, a slim tail seen from a hill at morning, a streak that crosses a child's field of view and becomes a memory resistant to age, a sunset that gains an extra band of colour because the upper air has borrowed a little light to scatter sideways. Photographers find pillars, arcs, and layered blues they have not seen in years. Musicians and poets find language for the way twilight lingers like a promise. Communities share these moments not to deny the science, but to live alongside it, translating watts per square metre into something humans can feel and keep. In the stronger, rarer branch, beauty aligns with competence. The same networks that notice and forecast also reassure and guide. Charts with uncertainty bands appear before rumours can grow. Small mitigations are in place before anyone needs to ask. The first confused posts online meet clear, local links that say, "Here is what changed, Kishimer, how much and for how long we expect it to matter." There is grace in that quiet choreography too, the ordinary heroism of planners and technicians whose names never trend, but whose steady hands keep routines intact. Across all branches, the unlikely and the likely are not moral categories. They are tools. Likely tells us where to put most of our attention. Unlikely tells us where to keep a shelf of plans we rarely touch. Both are informed by measurements, updated by experience and delivered in language scaled to the signal. When people see that pattern repeated, early notice, plain words, proportionate action, visible revision, their own private stories change. moving from omen or miracle to something kinder. A shared environment that occasionally nudges our margins and, in doing so, gives us chances to practice being responsive rather than reactive. Beauty is also the humility this teaches. A visitor that does not know we exist still manages to gather us under the same sky and ask quiet questions about preparedness, patience, and wonder. It draws lines between disciplines that often live apart. Plasma physicists speaking with agronomists, grid schedulers with sleep researchers, pilots with astronomers, teachers with forecasters. It reminds us that most of what keeps a city humming is not dramatic. It is the sum of 1,000 small, well-timed decisions made by people who trust numbers and each other enough to adjust a notch when the light tilts. If you look for a single sentence to hold the likely, the unlikely, and the beautiful together, it might be this: the universe usually deals gentle cards, and when it does not, it gives us enough time and signal to play them well. A faint traveller crosses our sky, and the most probable gift is knowledge, better models, cleaner tools, wiser expectations. The improbable gifts, when they arrive, are still gifts if we have prepared without panic. They reveal how strong quiet systems can be, how much beauty rests in competence, and how much meaning people can draw from the simplest kind of public spectacle. A shared look upward and a shared breath taken a little slower than usual because the light, for a while, is not quite the same. Departure is not a moment but a tapering. The visitor does not turn or wave, it simply keeps its promise to momentum. Night by night, its apparent speed across the stars slows, not because it is breaking, but because geometry is changing. The angle between us and its path widens, the distance stretches, and small motions project even smaller on our sky. Photometry sessions grow longer to catch enough photons for a single usable point. Exposure times creep up, tracking rates become more delicate. The object's point spread function sinks towards the background as if water were rising around a stone. The last clear measurements may be a handful of positions with larger uncertainties and a light curve that barely holds a period. Observers know this rhythm. You do not fight the fade, you lean into it, taking what the sky will still give while writing down cleanly what it can no longer provide. As the Sun-object-Earth angle changes, the phase grows and then shrinks again. If there was any coma, it subsides with the cooling. Non-gravitational accelerations driven by gas jets diminish first, then vanish into noise. Orbit fits revert to purely gravitational terms, and the hyperbola's outgoing asymptote locks in. That asymptote is a line you can name in numbers, a direction in right ascension and declination, a speed at infinity in kilometers per second, an inclination in the ecliptic and galactic frames. It is a forwarding address written in dynamics. In internal notes, teams write, almost ceremonially, A1 equals A, 2 equals A3, consistent with 0 within errors. A quiet way of saying the object has stopped speaking with thrust and is back to the oldest language, mass and distance. Data processing shifts from catch it tonight to make it last forever. Pipelines freeze versions, calibrations are audited, flap fields and bias frames are archived alongside raw images because future re-reductions will need the same environment to reproduce results. Astrometry logs include the star catalogues and software hashes used. Photometry includes 0 points, colour terms, and apex with diagrams. Spectral extractions store the solar analogues and sky windows. Polarimetry captures instrumental angles and depolarization corrections. These boring details are the difference between measurements that age gracefully and ones that cannot be trusted a year later. People imagine discovery as the bright part. Most of the useful life lies in careful, durable bookkeeping that lets others stand where you stood and see what you saw. The cadence of follow-up narrows to specialists. Big telescopes give the object a last look in the reddest filters where detectors are most sensitive and the sky is darkest. If a space observatory was in play, it fits a final visit into a window squeezed between higher priority programs, often to finish a phase curve or to try one more spectrum in a band that was weathered out earlier. Radar, if anyone hoped for it, is usually off the table, fast, small, and far as a combination radar dislikes. Occultation campaigns, if geometry and luck permit, may get a last attempt, but the path narrows and the prediction spreads widen. 1 or 2 chords in the dark would be a triumph. In most cases, the farewell is statistical. The uncertainties contract to a stable set, the residuals look clean, and the ephemeris page acquires that telling phrase, "Further observations are unlikely." Dust, if any was shed, takes longer to leave than its parent. Trails elongate along the orbit. Differential radiation pressure sorts grains by size, drawing graceful, size-dependent fans that only deep stacks can reveal. Earth's path may intersect the thin stream months or years later, and meteor radars will still be listening. If counts spike on schedule and speeds match predictions, the debris is logged into the shower catalogues with a parent labelled by its interstellar designation, and a confidence flag that will improve if the pattern repeats. If counts do not spike, the non-detection is not a disappointment. It is a constraint that tightens models of grain sizes and ejection speeds. Either way, the sky keeps the appointment, and the record keeps the appointment time. Inside the computers, the orbit solution gets its adult clothes. Short arc tricks give way to long arc formalisms. Covariance matrices shrink and then stop shrinking, an honest signal that the information content is fully harvested. The record now includes multiple coordinate frames, ecliptic for solar system work, equatorial for telescopes, galactic for those who think in spiral arms. The outgoing state vector is propagated forward, not for our benefit, but for completeness. A gesture that says, if any civilization a long way off wants to know who visited us on this date, this is the line you should look along. It is not messaging, it is indexing in the library of motion. Papers and reports move from letters speed to full article thoroughness. Early notes, we saw, we think, are now expanded into we measured, we tested, we rejected, we accept within these bounds. Light curves get modelled with single and 2 period fits to check for tumbling. Spectra are stacked and compared to taxonomies from our comets and asteroids, with the caveat that taxonomy is a hint, not a verdict. If thermal data exists, it is reconciled with reflected light to pin albedo and size within a smaller rectangle. Where there is disagreement, the disagreement is the heart of the paper. Where there is concordance, the value lies in how generalizable it looks when set next to prior interstellar visitors. One object cannot write a law, but it can draw a line that the next object might cross or follow. Public attention has already moved on. That is not cynicism, but ecology. News cycles are built for novelty. Science is built for accumulation. What remains in the open for everyone to see is a few clean plots, a summary page that will be cited by students who are children now, and perhaps a handful of images that enter the quiet museum of space photos people revisit when they need to feel large and small at once. In classrooms, a teacher may click through a simulation that shows the inbound and outbound arcs and say to a room of blinking eyes, "This one came from outside and left again, and here is how we know." If 2 students ask good questions, the mission succeeded a second time. Instruments pick up souvenirs before they are powered down for the night. Survey teams compare their false positive rates before and after the campaign and find that their machine learning filters now ignore a class of artifacts they once chased. Orbit solvers are a fraction more stable at high speeds. Prediction pages render uncertainty cones more clearly. Sky quality monitors add an aerosol layer that helps energy forecasters, a gift from a science that never promised to help power bills and did anyway. Amateur networks gain confidence and coordination. A small observatory that thought it had nothing to contribute learns that timing and calibration make its light curves as sharp as those from larger mirrors for targets in a certain magnitude range. All of this is leaving too. Not the object, but the friction we just sanded down in ourselves. Beyond the heliosphere, beyond the planet's reach, the traveller's conditions become simple again. Sunlight dwindles, temperature approaches the low plateau set by distant starlight. and the cosmic microwave background. Cosmic rays resume their patient work on surface chemistry. Micrometeoroid hits resume their patient work on texture. If a crust sealed deeper ices near our sun, that crust thickens a little in peace. The spin state, nudged slightly by any gas jets it used to wear away uneven warmth, now changes only by the tiniest torques from re-radiation and asymmetric micro-impacts. The object returns to anonymity, which is the default state of almost everything. Galactic dynamics folds the path into larger motions. In the local standard of rest, the visitor has a small peculiar velocity. In the sun's frame, it carries the asymptotic speed we measured. In 100 million years, it will have crossed arms of different densities, and the ledger of small stellar tugs will have lengthened. It might pass within a light year of another star and feel its path bend a degree or two. In rare cases, after ages, it could be captured into a wide, temporary orbit in some other system, to be heated again and asked again what it is made of by instruments we cannot imagine. Odds are stronger that it will remain a drifter, part of a diffuse population of star-forged leftovers that keep the galaxy honest by reminding it that not everything that forms in a disk stays in a disk. For us, leaving closes with synthesis. Catalogues add a row, review talks add a slide, proposals add a paragraph that says, "Next time we will catch the onset of activity earlier," or "We are now sensitive to smaller amplitudes in rotation." Engineering teams draft small upgrades, a faster scheduler for time-critical observations, a wider dynamic range for detectors to cope with high sky motion without smearing, a better way to forecast the balance of direct and diffuse light for energy grids. Education teams write a short module that turns the object's arc into a math exercise about conic sections with real numbers and real uncertainties. Museums build an exhibit that lets people move a slider labelled eccentricity and watch a dot fall in and out. Children discover with their hands why a greater than one means goodbye. Silence is not empty after the visitor leaves, it is filled with a residue of understanding. We keep a list of what did not happen, no unexpected accelerations after venting ceased, no late dust surge on the outbound leg, no colour shift that would demand exotic chemistry, and what did, a period measured within minutes, a colour slope that sits near the range of processed organics, a V infinity that matches the modest speeds of objects bound loosely to the local standard rather than to a specific moving group. We keep a list of what we still do not know because it is honest to do so. The exact shape because occultations missed. The precise albedo because thermal data were thin. The depth of any crust because activity was too faint to model uniquely. These lists make leaving feel like part of the work rather than its end. If you step outside on a clear night after the last observation is logged, nothing announces the end of a chapter. The constellations return to their ancient stillness. The dome looks the same to every animal that has ever noticed it. Somewhere along a direction you could point to if you had memorized a few coordinates, a stone you helped weigh is a little farther away than yesterday, and tomorrow it will be farther still. That is all, and it is enough. Leaving, in this sense, is how knowledge keeps moving. A thing enters our circle of light, we make a careful sketch, and then it passes beyond the edge again, while the sketch remains. The edge, for a moment, is larger than it was before. Then we wait, instruments quietly ready, language cleaned and stored, for the next traveller to cross that edge and teach us how to draw it a little wider. What remains is a change in posture, the way you stand with the world when you know visitors can cross it without warning or fuss. The habit of measuring before speaking stays. The comfort with uncertainty stays. The sense that preparation is a kind of neighbourliness toward each other and toward tomorrow stays. You discover that learning to read faint things in the sky teaches you to read faint things in yourself, the small anxieties that soften when named, the little curiosities that grow when given time, the patience that appears when you stop asking for a conclusion and start asking for the next honest piece of evidence. None of this needs an event to continue. It folds into the quiet fabric of days, like the way you now glance at the sky, not to see spectacle but to notice light, angle, clarity, and the gentle truth that everything is in motion. Tools endure. A camera meant to track a dim object becomes the same camera that documents a community garden at twilight, and the calibration that once corrected star colours now helps an artist keep their print work faithful under changing light. A grid operator's model that learned to incorporate aerosols now helps forecast a low-cloud day more cleanly. A teacher's lesson on conic sections remains in a drawer, ready to turn numbers into curves for the next group of students who need to feel math touch something real. A farmer's notebook keeps the adjustments, sowing a week earlier here, using a variety with a shorter maturity there, so that when a season bends, it bends within plans, not beyond them. The traces of the visitor live inside these tools and habits, not as labels, but as slight improvements that make ordinary work more reliable. Language refines. You keep words that carry scale gently. Veil, phase, haze, margin, ensemble. You let go of words that crowded your breath. You learn to say we saw or we infer or we're testing like rungs on a ladder. You can climb or descend without embarrassment. This language migrates into places that never needed astronomy to improve. A town hall, a clinic, a studio, a kitchen table conversation about what the next month might feel like. The tone becomes a kind of civic weather, modest, precise, willing to update, so that when the next unknown visits, you do not have to build a new voice to greet it. Collections grow. Data archived with care becomes a library that new eyes can enter. Observations from small telescopes sit beside the spectra from major facilities. Timing logs from backyard stations sit beside LiDAR profiles and satellite charts. The dignity of contribution becomes obvious in the way a plotline thickens when one more point lands exactly where it should. Children who once saw only a streak of light now see a chain of custody, who measured, who checked, who shared, and how community makes a truth sturdy by carrying it together. Museums and science centres gather a few artefacts. A shutter that clicked 1,000 times, a notebook page with a first ephemeris scribble, print of a faint tale that required an entire town to turn off its lights for an hour. And these objects explain themselves without speeches because they show attention made physical. Rituals persist. Evening walks that began as a way to look up continue because they turned into a way to look around. A quarterly dim day drill survives because it saves money and smooths nerves, even in bright seasons. A morning lamp on a timer keeps its place by the window, not because the sky is unreliable, but because the person using it has learned that keeping sleep steady is a gift to everyone they'll meet that day. Community sky notes remain pinned in places you pass. A library board with last week's meteor counts and aerosol index. A sidebar in the weather forecast that shows not only temperature and rain, but also the clarity of the high air. A short paragraph explaining why sunsets looked different last month, in words a child can use. Values sharpen. Wonder stops competing with realism. It partners with it. The same attention that makes a spectrum meaningful makes a conversation kinder. The same care that aligns a telescope makes a schedule humane. You notice that accuracy of words, of forecasts, of expectations is a form of hospitality. It welcomes other minds in, it lowers the volume on fear. It makes space for people who are strong in different ways. The technician who hears a motor's health, the grower who reads a leaf's colour, the dispatcher who can feel load shape in numbers, the student who finds just the right metaphor to tie a sky plot to a feeling. The visitor did not bring these strengths, it revealed them. Scale becomes intuitive. You no longer need to be told that a few percent is not the same as a catastrophe. You learn to feel the difference between a local variance and a global drift, between an anecdote and a pattern, between a single spectacular event and a quiet forcing that matters because it lasts. This sense moves with you into news of every kind. It gives you permission to keep a steady heart in a loud world and to spend your attention where it can do actual good, on the small acts that accumulate. A forecast sent on time, a reminder to water at dawn during a slow-growing week, a lamp turned on for a neighbour who needs the morning brighter. The arts keep what numbers cannot. A painting catches the way a thin veil makes the sun's edge bleed into the sky by a hair's breadth. A poem records how the first meteor in a child's life sounded in the throat of the adult who tried to name it. A piece of music uses a sustained note to hold the feeling of a twilight that refused to end on schedule. These works do not argue with measurements. They archive the part of the experience that statistics cannot contain. They become ways to return, gently and without hurry, to the moment when you realize that other star systems can drop a pebble into our pond and send ripples through our routines and our imaginations at the same time. Institutional memory develops muscle. Agencies document what worked and what wasted time. Universities write field guides for cross-discipline collaborations so that the next time plasma physicists and agronomists share a table, they do not waste a week learning each other's units. Newsrooms build checklists for uncertainty so that editors ask for scale and source before headline and art. Co-ops and utilities and clinics add small standing budgets for adaptation that do not require emergencies to unlock. The machinery of collective response becomes less theatrical and more like good carpentry. Measure twice, cut once, sand the edge that catches. Personal maps broaden. You form a simple picture of where you live in the galaxy, not as coordinates and velocities you can recite, but as a lived sense that the sky above you is not a dome but a volume, and that volumes welcome travellers. You keep a mental note that beyond the weather there is climate. Beyond climate there is radiation and dust. Beyond those there are stars and their winds. Beyond those there is a disk that once nursed our sun and then let pieces go. That map helps you place yourself without shrinking. You become larger by being more situated, not more important. Trust, once tested, becomes a practice rather than a hope. You know which sources tell you what they know and what they do not. You know how long it takes for a rumour to be corrected if it matters. You know how to check a chart before forwarding a claim. You know that if something truly concerning is afoot, it will not arrive only in the form of dramatic adjectives. It will arrive as a coordinated chorus of consistent numbers measured by different hands saying the same thing. That practice of trust spills outward, from observatories to hospitals to water boards to schools, because the muscle you used here is the same muscle you use there. Gentleness grows. By watching a small body obey simple rules for a very long time, you relearn that patience is not passivity, it is engagement paced to reality. You notice where in your life a tiny consistent push would outdo a panicked shove. You make a list that includes nothing grand. Put the phone on the table during breakfast, step outside for 5 minutes of real sky, even on busy days. Choose one forecast to check and stick with it. Learn the names of 2 stars near your home so the night has a skeleton you can recognize. These are not sentimental tasks. They are calibrations, like the ones you apply to instruments before measurements so that numbers will mean what they say. Finally, gratitude takes a practical shape. Not a vague glow, but a decision to keep certain doors oiled. The door to the archive, the door to the classroom, the door to the roof where a tripod lives, the door to the community hall where somebody will set up 2 lamps and talk about sleep and morning light on a rainy week. You understand that what remains after the night depends on these doors staying easy to open. Visitors will come again from between the stars or from the long corridors of our own system. Some will be bright, most will be shy. You'll be ready to meet them with a pencil, a plan, and a group of people who have learned almost casually how to be calm together. And that calm will not be empty. It will be filled with the ordinary durable work of attention that lets knowledge stick and lets wonder visit without asking permission to stay. If you're still with me, listening in the soft margin of night where thoughts loosen and the world grows quiet, thank you. We have followed a faint traveller from first notice to last trace, turned scattered photons into meaning, and watched how a small passing thing can open large, steady rooms inside us, rooms for patience, for careful words, for preparation that feels like kindness. Maybe you felt it too, the way curiosity can be a lullaby when it moves at a human pace. the way numbers can hold your hand when stories run ahead, the way light itself, thinned, battered, returned, can teach us how to let go without losing anything worth keeping. As you settle down, let your attention widen just enough to hold the sky you cannot see. Somewhere above your roof, the same quiet laws are at work, guiding stones and dust and the long breath of starlight. Somewhere a telescope finishes a final exposure, a small green progress bar completes, and an instrument goes still until morning. Somewhere a student learns why an open curve means a visitor will not return, and a farmer sets a notebook aside with a small adjustment for a slightly dimmer noon. Somewhere a grid dispatcher slides one more slider a notch and then exhales, because the forecast matched and the light stayed on. The world is full of these ordinary unheralded alignments, people meeting the universe with competence and humility, and you are part of that fabric simply by caring enough to listen. If tonight brought you a calmer way to think about surprise, hold on to that. If it reminded you that most outcomes are gentle and most changes are workable, keep that nearby. If it gave you a language for uncertainty, we saw, we infer, we're testing, use it tomorrow in any place that needs less heat and more light. If it nudged you toward one modest habit, checking a simple chart before sharing a dramatic claim, opening the window to meet the real sky for 5 minutes each day, placing a small lamp on a morning timer to anchor steady sleep, let that habit take root the way dim starlight still finds your eye, patiently and without argument. I'd love to keep building this quiet archive with you. If this kind of slow, thoughtful journey helps you rest and still makes room for wonder, please subscribe, leave a gentle note about what stayed with you, or share a chapter that spoke to a friend who loves the night. Your small actions tell the platform to keep sending these calm stories your way, and they help this channel remain a soft corner where we can return when the day is too loud. Suggest the next path you want us to trace, another traveller, a forgotten weather of the upper air, a question about time or light or memory, and I'll map it with the same care, the same unhurried voice, the same promise to measure first. For now, let your breathing match an easy rhythm. In for a slow count, hold for a moment that feels kind, out a little longer than you breathed in. Let your shoulders drop. Notice the weight of the bed, the coolness of the room, the small sounds that mark safety, the far hum of a street, the faint tick of cooling pipes, the quiet a house makes when it understands you are going to sleep. Imagine the sky above you as a wide, calm ocean of dark with thin currents of dust and light sliding through it, everything moving lawfully, everything in its time, everything content to be what it is. If thoughts arrive, let them pass like meteors, brief, beautiful and icky. If a worry insists, place it on a shelf labelled, "We'll measure in the morning," and trust that morning always brings better instruments. When you wake, hours from now, not yet, there will be work and conversation and small chores that make life human. You will carry with you a trace of this night, the sense that you live in a larger neighbourhood and you belong in it, that being ready is not the same as being afraid, that wonder and realism are not rivals, that even a faint dot can be a teacher if we let it be. And if the sky is clear, maybe you will step outside and look once, not for a spectacle, but for a simple alignment. You, the horizon, and a piece of the cosmos that kept moving while you slept. That is enough. It always was. Thank you for watching, for listening, for resting here. Thank you for the trust of your attention. May your night be easy, your dreams untroubled, and your morning bright in the ways that matter most. We'll meet again under this sky or another, and trace another quiet arc together. Until then, good night, sleep well, and remember, the universe is patient, and we can be too.